Okay guys, let's go ahead and get started. So today we're going to finish up all of domain 3. Again, since you guys have been here for the entire class, if I do see some repeated things, we probably won't touch on them over and over again because I do want to get through domain 3 today. So we're just going to go till we finish that today. We left off at domain 3.1.1 yesterday. So I'm going to begin on domain 3.1.2. Given a scenario, troubleshoot common issues with identity and access management. And now we're going to go over authentication and authorization. Okay, and then here are the exam objectives we're going to go over. And again, from a high level, we're just going to go over all these different authentication authorization protocols here. I would love to deep dive into OpenID and how Kerberos actually works and how that ticket grading ticket system integrates into Active Directory along with LDAP and NTLM. Especially when we get to 802.1x, as a network engineer, I set that up all the time using Cisco ICE. But they're just going to look at things at a high level here as it fits this exam objective, just troubleshooting identity access management. Okay, so again, we're going to talk on attestation. This is a formal process of reviewing and validating user access rights to ensure they are still appropriate for a user's current role. In large organizations, users frequently change positions, projects, or departments. Without attestation, users may retain access to systems and data they no longer need, creating unnecessary risk. Yeah, this happens a lot. I was working at Anduril for a couple months, and my buddy that helped me get the job, I think he's in his third position now, and it's been 2 years. And it's not really it's not a bad thing. It's just growth throughout those companies, and it was different business lines and departments. So I'm sure in that organization that runs like oil, they're gonna make sure to do their proper account audits and say, hey, does this user need these rights? So attestation is usually performed on a scheduled basis and often involves managers, system owners, or compliance teams. It's not a one-size-fits-all. Sometimes in a smaller organization like where I'm at now, it may just be that one ISSC that says, okay, I need to do some quarterly attestation. Let's look into my ICE server. Let's look at my Active Directory. Cloud IAM and trust policies. So when we talk about the cloud, the very perimeter of the cloud when it comes to security is IAM. It is that identity access and management. Without protecting, your console access, without protecting the APIs or whatever calls you're making from Terraform to get into that cloud service and your tenant to, provision and monitor your resources, you need that protected. You need good access control there. So cloud IAM access and trust policies. So IAM relies heavily on policy-based access control rather than static group membership. A little bit different, and again, I speak from my experience in Azure, where in Azure, we can apply role-based access control and Azure policy to resources, not just users and service accounts, but actual objects, which, yes, is a little similar to how we did it with group policy and a regular on-prem Active Directory domain. But it's in the cloud, it's RBAC and Azure policy. I don't really know what they do in AWS and GCP. It's pretty much just all policy-based IAM for all these different service accounts and objects as well. So trust policies establish relationships between identities, accounts, or services, allowing secure cross-account or cross-service access. Now that term trust policies, I believe they're just doing that as a high-level term to describe what every cloud service provider does when it comes to protecting their identity access management. So misconfigured policies are a leading cause of cloud security incidences. Policies that are too permissive may grant excessive access. Where's my mic at? There we go. While overly restrictive policies can prevent legitimate operations. Logging and monitoring, we've talked about this a lot, but when we're troubleshooting identity access management, we need to do some log dives sometimes. We need to understand why something didn't authorize me. When I deal with TACX, on a network, this happens all the time where even from the switch, I'll look at my TACX logs and my debugs and say, okay, I'm not getting access to this, but is it stopping me at the authentication phase or the authorization phase? That's really going to matter, and that's going to be where I start my troubleshooting, because if it stopped me at the authentication phase, that means my username and password is wrong, or my certificate is wrong, or I'm not even reaching it. You can even check that as well. And that could be from the supplicant device or actually the authenticator. Now, typically in a broad enterprise where cybersecurity is ingesting all these logs, you kind of start from that authenticator, that centralized authenticator, and then branch out to the end devices. So troubleshooting, Depends who you ask. Sometimes starts at the endpoint. Sometimes that centralized authenticator authorization service. Typically, though, it's easy, really easy to monitor that one and ingest its logs, and that may tell you the full picture sometimes. So IAM-related logs include authentication events, authorization decisions, token issuance records, privilege elevation attempts, and federation activity. Okay, PIM. So privilege identity management controls how and when elevated privileges are granted. So this could be like just-in-time permissions, like JIT is what it's called, JIT, where we say, we're going to do privilege identity management, and this is something you can configure with that P2 license in Azure actually directly, like on the console, and say, hey, this user, we're going to give them just-in-time permissions, and you'll configure that under your PIM like processes, that privilege identity management. So PIM provides temporary time-bound privilege elevation with approval and auditing requirements. When I do my Azure classes, this is actually exactly what I set up. I pretty much say that for that week, I give them access to my Azure portal, and I let them pretty much have free reign. Now, at the end of class, I tell them, hey, delete your resources, and then I go through and I actually delete their entire like tenants out of there because I don't want to cost myself a bunch of money. But anyways, that's exactly what I do, and I only give them access to it for literally that week. So then after that, I'm like, hey, if you want to practice Azure, you got to like practice on your own time, or your company has to pay me a lot more money for you to be building VMs in here that could be cost, building a big bill. Okay, more authentication and authorization. So now we're going to go over SAML and OpenID Connect. Okay, so SAML is a federation protocol that allows identity information to be securely exchanged between an identity provider and a service provider. It enables single sign-on by allowing users to authenticate once and access multiple systems. So you're going to notice with like OpenID, SAML, OAuth 2.0, they're all going to be like these single sign-on federation protocols that allow you to access a single account to access other services. Now, how those protocols work, the actual the underbelly of it, we can't get into too much. You just got to know at a high level what it does. So SAML is a federation protocol that allows identity information to be securely exchanged between an identity provider and service provider. Now, we are talking about troubleshooting here. So what are some common SAML issues? This includes certificate mismatches, expired signing certificates, incorrect service URLs, clonk synchronization problems, and mapping errors, attribute mapping errors. So just pretty much like the basics of a user account. You think, why is an authentication service not working? Well, is it the timing? Is it the clock? Is it a URL that's bad, that's not available anymore? Were we making an API request to a backend API that's no longer available? Do we have certificates that aren't matching? Certificates that maybe not matching with the service account, they're not tied together, so we have an authentication error. And a lot of those are going to be, when we talk about OpenID Connect or OAuth 2.0, it's going to be a lot of the similar things. And a lot of times it's like, do I have the correct API key or client key in there? Okay. OpenID Connect builds on OAuth 2.0 to provide authentication using lightweight JSON-based tokens. It is widely used in modern web and cloud applications. Failures typically involve token expirations, incorrect scopes, or misconfigured redirect URIs. So more protocols. So multi-factor authentication. We've talked about this a little bit. Multi-factor authentication is three main categories, three main factors. It's something you are, that's your biometrics, that's your face ID, fingerprint scans. That is something you have, so that's something you own, maybe that was given to you by a company. Most common one is your cell phone that does authenticator, right? And then something you know, which is something you created. So that's a username, that's a password, that's a PIN. SSO, single sign-on. This allows users to authenticate once and access multiple applications without repeated logons. So what's the troubleshooting there is pretty much, there's really only two things that can be wrong. It's either the protocol that's enabling SSO you need to dive into. So that's looking at OAuth 2.0, OpenID, or SAML, depending which kind you are using to build that trust between you and the centralized identity provider, doing those API calls, tokens, whatever. So that's step one, look at that process, or see if the identity provider is down. So it's really just, hey, am I still building a trust between them using SAML? Do I still have this backend trust built to this identity provider where they say, yes, I'm a good relying party, I'm a good third party that will, we allow to use our identification services? Or is it just this, does that user's Gmail account messed up and you're integrating Google? So you got to look at that. Now, from an enterprise perspective, when we talk about SSO, I think of it from an admin's perspective. So like traditional enterprises that we used to work on, if you guys have been in IT a while, I had access to a call manager, I had access to NetApp, I had access to vSphere, the Cisco UCS chassis, like it's like its version of DRAC if you're used to like Dell iDRAC. What else? ICE. A lot of these different, administrative tools that I had an account for each one, that call manager would manage itself, that vSphere would manage itself, that Cisco ICE would manage itself. And then we started saying, why do we need to do this when these tools give us LDAP synchronization and a backend to integrate into Active Directory? So then once we integrated that to Active Directory, we were able to set permissions on that. All of a sudden, we had a single sign-on experience where I could use just my admin account that I used to log into the domain or to do enterprise domain administration. I can now use that to log into my Cisco Call Manager, to log into Cisco ICE. So that's a single sign-on experience using something like LDAP within the enterprise. Then we have Kerberos. So Kerberos is a ticket-based authentication protocol commonly used in enterprise environments. It's used in Active Directory. It relies on trusted key distribution centers and synchronized system clocks. Common issues include time drift, because it's a ticket-based. There's something called TGTs. It's time granting tickets. So your timing is actually very important when you have domain services running, Active Directory domain services on-prem. So common issues, again, include time drift, DNS misconfiguration, service principal name conflicts, and expired Kerberos tickets. Okay, so this one's kind of funny. SAE is actually a Wi-Fi protocol that's part of the Wi-Fi Protected Access 3. That's the newest way to do Wi-Fi encryption. When we do WPA3 personal, where you log into a wireless local area network, so you connect to an SSID and you put a password in and you're getting granted access to a network. What SAE actually allows us to do is get PFS, perfect forward secrecy, that helps us protect against brute force attacks. And the way it pretty much does is that each time that it sends a message, like a data frame to the wireless LAN, to that access point to then connect to that wireless LAN, it's going to have a new initialization vector so that you can't get brute force, or you can't do a man-in-the-middle attack like in previous Wi-Fi protected access encryption methods. So it gives us brute force protection, and PFS is what it's called, perfect forward secrecy. And then we have PAM, that's privileged access management. This is where it's like you have imagine you have one admin account that all 5 of your network techs use to go run show commands on the switch. But each time a network tech uses that admin account, they have to go to like maybe a jump server and then use that admin account. And we're logging and monitoring that. We're saying, okay, we know that network administrator 1 is using the account at this time. We're going to log and monitor that. That's really what it is. But it allows you to do things like credential vaulting, session monitoring, and access brokering. So it's kind of a little bit more control over maybe a user that shouldn't be as trusted with their elevated permissions. Now, if someone made me do this, like a shared admin account, I'd be pissed because I'm like, no, I want my own thing. I don't want to, manage PAM just so I can manage it myself, right? But anyways, that's what PAM is. It's pretty common, like especially with like tier 1 help desk and like civilian world, some sort of PAM. And then OAuth. OAuth allows applications to access resources on behalf of users without exposing credentials. OAuth issues frequently involve incorrect grant types, expired tokens, and scope mismatches. Okay, EAP. This is going to be used again in like that wireless environment and like network access control. EAP, Extensible Authentication Protocol, is a framework that supports multiple authentication methods commonly used in network access control. It's a framework, so we build on top of it. So like we can use EAP for 802.1x. We can use EAP and put TLS on top of that for when our wireless lightweight access points actually connect to a wireless LAN controller. We can put that additional encryption on it for when they do their join process. So it's just a framework where we can build security on top of it for authentication. Identity proofing. So identity proofing verifies that an individual is who they claim to be before issuing credentials. This is just saying, it's just identity access management at the end of the day. However you're proving it, whatever you have to do to prove an identity before we issue you a certificate. We do this. So my CAC, when I had to go get my CAC card, I had to get a sponsor. So my GS, I don't know what he is. It's like a 14, I think. He's like in charge of our program. He said, yeah. So like my company, as you guys know, right? Your contractors, you know this process. My company put in for a sponsorship request because I'm a new employee. The sponsor had to agree to it. It got sent to whatever system it is. And then I got an email saying, hey, fill out your information and make an appointment at your local DEERS office because you've been sponsored. I go to the local CAC office. I need to get 2 forms of ID. They look to see that sponsorship paperwork is there. They say, okay, let me check your passport. Let me check your social security or your license. You are who you say you are. That's identity proofing. That's it. And it just seems so common now. You go to the DMV, they do identity proofing. But you may need 2 forms of ID to get like a license or something like that. I just recently did that too. So sometimes it can be that manual human process. Okay, then IEEE 802.1x. This is network access control. This is the protocol that enforces, network NAC. So it enforces authentication before granting network access. It is widely used for wired and wireless access control. Common problems include radius misconfiguration, certificate trust issues, and incorrect authentication method selection. So we use this in conjunction with a AAA protocol like Radius to actually do our authentication authorization. And then accounting, of course. Okay, let's go ahead and do our quiz. So this is going to be domain 3.1.2. Let me bring the chat up here. Okay, question 1. Let me write it out over here. An enterprise wireless network uses IEEE 802.1x with EAP TLS for authentication. So that's just adding security on top of that authentication process. Several users report that they can see the wireless network but are unable to connect. Authentication logs indicate repeated failures during the certificate validation process. Which of the following is most likely the root cause? Yeah, certificate validation. So it's kind of funny. So since we're using TLS, it's like which certificate? Because that requires PKI, right? If you want it trusted, unless you don't want it trusted, then we just can use those encryption cipher suites. Anyways, so repeated failures during the certificate validation process. Something wrong with our certificates. Maybe it's our issuing certificate servers giving us bad shit, or it's expired. Incorrect VLAN assignment after authentication. That actually is a common problem though with 802.1x if you guys ever worked with it. Like getting the wrong VLAN that doesn't line up to the right DHCP pool, but I don't think that's our problem. OAuth is not used in that. Expired or untrusted client certificate authority certificates. Yeah, that's probably the only thing that makes sense. Missing single sign-on configuration? No, that don't make no sense. So yes, it's C. Good job, guys. Question 2. Let's see. Privileged access. So a security administrator is reviewing privileged access management controls after discovering that an administrator account retained elevated privileges longer than intended. The organization uses time-bound privilege elevation with approval requirements. Which of the following failures would most likely allow elevated privileges to persist beyond their approved duration? All right, so let's think about this here. They're using PAM. After they retain elevated privilege longer than intended. Time-bound privilege elevation with approval requirements. Sounds more like PIM to me. That reads more like PIM than it does PAM, but okay. Which of the following failures would most likely allow elevated privileges to persist beyond their approved duration? Yeah, they don't do proper attestation. They don't do a proper account auditing. Okay, let's look at our answers here. So A, improper privilege expiration or revocation configuration. Yeah, the revocation being the key word there. That's probably going to be it. Missing attestation reviews. Well, attestation is really more for just accounts, period. But I mean, that is an account. Lack of multi-factor authentication enforcement and misconfigured federation trust. So we know it's not C or D. Let me read this. After discovering that an administrator account retained elevated longer than intended. But they do attestation in some way, if that's a policy. But it's a failure, right? So it's just like a misconfiguration rather than us missing an account audit. Okay, yeah, I'm going to go with A here. I'm going to agree with you guys. Let's see what it says. I want to read the explanation on this one. Okay. So yeah, A, privilege access management system are designed to grant elevated privileges for a limited period of time. When privileges persist beyond the approved window, the most direct cause is a failure in privilege expiration or revocation controls. Misconfigured time limits, misconfiguration. Okay, let's see this. Attestation reviews identify whether access should exist at all, but do not control real-time privilege duration. Okay, that's true. That's what we read in the slides too, that it said, it's like pretty much attestation, just from that definition, kind of, to me, reads like, are you actually enforcing least privilege? Are you actually enforcing the principle of least privilege? So you put it in that context, it makes sense why that wouldn't be the answer. Okay, question 3. An organization has implemented a cloud-based single sign-on solution using federation. Users report that authentication is successful, but they receive access denied. Errors when attempting to access a specific cloud application. Logs show that authentication tokens are being used correctly, but authorization fails at the application level. So we're getting authenticated, we're verifying identity, but we're not getting permissions to this application or at the application level. Which of the following is most likely to cause this issue? So it's authorization, so it's always going to be like permissions, your role, your policy that's applied to you. So expired authentication certificate, no, we already authenticated, so it's not authentication. This is an authorization issue. Incorrect role or claim mapping in the cloud IAM policy. Kind of going to be it. Yeah, exactly, Masood. It's authorization, that's the key thing there. Time synchronization issues between the identity provider and service provider. If there was time issues, you probably wouldn't even authenticate, so no. And then multi-factor authentication, it's again authentication. So yeah, B is the only thing addressing authorization. Yep. All right, awesome. Another 100%. Let's go. All righty, let's go move on to domain 3.2.1. Is that it for just, okay, one slide for here? Yeah. All right, so domain 3.2.1. Given a scenario, analyze requirements to enhance the security of endpoints and servers. So this is pretty good. We're just going to go over a bunch of different ways we can really just protect our endpoints. So let's go ahead and do it. So application control. So application control is a security mechanism that determines which application is allowed to run on an endpoint or server rather than attempting to identify malicious software after it's already been executed. So this is us building our whitelist or our blacklist or what we call our allowed list onto our endpoints. However you do that. If you do that through group policy, if you do that through an MDM solution like JAMF, JAMF, traditional security models often rely on blocking known malicious applications, but application control takes a more proactive approach by allowing only explicitly approved applications to execute. It reads just like a whitelist, if you know what that is, or an allowed list that pretty much has like an implicit deny at the end. Okay, EDR, you've heard me talk about this a lot, so let's finally go over it. So endpoint detection and response, for EDR, it's a security technology designed to continuously monitor endpoints for suspicious activity and provide tools to investigate and respond to threats. So this differs in traditional antivirus, anti-malware. It's a little bit, we say smarter, and what we really mean by that is it's able to do heuristic-based scanning automatically and able to build that user behavior baseline automatically at the endpoint and really not take up too much of your like CPU and RAM like anti-malware and antivirus used to do, because it would scan these large signature files and go through every single file. EDR may have the capability to do that, but it's there to detect advanced threats, which has to use something like heuristic-based scanning. Build a behavior baseline for your computer. Look at what it is normal operation, what is normal applications to be used, and then trying to detect it based off network connections, application use, what may look suspicious. So yeah, EDR analyzes behavior. That's the main difference. Let's do this thing. When suspicious activity is detected, EDR solutions generate alerts and often provide automated manual response capabilities. Yep. I just want to read that last one. All right, event logging and monitoring. So event logging and monitoring are foundational components of system security. Logging involves recording system events such as logins, file access, configuration changes, application activity, and security alerts. So endpoints and servers generate a large amount of log data, this big data. But these logs can provide a record of actions taken on the system, and it essentially helps us build our case, right? Think of us as detectives here. It helps us build, again, that baseline, what looks normal, so we can look for deviations. But also, those logs help us with compliance, seeing what version control we're on, or excuse me, what version we're on, so it can help us with version control. And then, of course, with like forensics. So if there is an incident and we're already ingesting logs into us, not only do we have to take a snapshot of the computer, and if something messes up there, then we also, like, or we mess up our data dump on the actual endpoint that got exploited, well, maybe we still have a centralized log that was damn near synchronous replication between. So that can help us. So without proper logging, attacks may go undetected for long periods of time. Endpoint privilege management. So endpoint privilege management focuses on controlling administrative privileges on endpoints and servers. Many successful attacks occur because users or applications have more privileges than necessary. So all we're saying here is, hey, make sure you're enforcing the principle of least privilege. And enforcing it not just on user accounts that may live on a system, because we may have some IoT devices, we may have had some local admins that we haven't disabled yet, which we need to go do that, some hardening, but system access, domain joined computers, whether that's in the traditional Active Directory or Intune, they join a domain, they join some sort of system that is going to apply policy to them as well, which at some level gives you privileges. And so we don't want to be victim to a privilege escalation attack because of that, a server's account running on there that a hacker exploits, things like that. So we want to make sure we're doing our audits. We want to make sure we're getting rid of those local admins, things like that. Attack surface monitoring and reduction. So I love that, attack surface monitoring. Everything's our attack surface. So whether I have, a printer or a user's cell phone and a nice lockdown enterprise while still being highly available, we'll have things like MDM, vulnerability scanners, log aggregation using like Splunk. We'll have our firewalls, we'll have our proxy servers that are kind of doing all this monitoring for us, and it's up to us to configure all these devices in a way that gives us the most clear view. Now when it comes to reduction, that is reducing the attack surface as best we can. So that's getting rid of things that aren't necessary. And what I mean by that is not always hardware. That could be in the software. Disabling ports, protocols. That's where our scans come into play, where we do like Nmap scans or a Nessus scan that says, hey, this device is like open on FTP. Why? Do we need to shut it down? And that reduces our attack surface there. Also the human element. Some companies could implement like a social media like policy that says, don't be posting about all the cool technologies you're using, things like that. That reduces attack surface. That's not giving us our attackers an easy footprint or an easy way to do reconnaissance and start footprinting our network or our enterprise. Hips and HID. So we talked about intrusion prevention, intrusion detection. We talked about it kind of more in the inline network way or in a tap or an active state on the network. But we also have hips and HIDs that live on the endpoints that we can install directly. It can be part of an antivirus, anti-malware. It can be part of an EDR, XDR solution. Guess what? The definitions pretty much are the same. Intrusion prevention system on a host does what? The exact same thing it did on a network. It prevents while also detecting and alerting. HIDS does the same thing. It just alerts. It just detects. Just logs. Okay, anti-malware. This is specific. So anti-malware, the definitions get real foggy sometimes between antivirus, anti-malware. So we're going to just go over this exactly, what it protects against exactly. So anti-malware software is designed to detect, prevent, and remove malicious software such as viruses, worms, trojans, ransomware, and spyware. So modern anti-malware solutions use a combination of detection techniques, including signature matching, heuristic analysis, behavioral monitoring, and machine learning. And you may be saying, well, Johnny, you just told me EDR does this. Yes, the lines are getting very blurred nowadays where, you just think about it from a capitalist perspective. If I'm an anti-malware solution, that's what I say. I'm anti-malware. So I'm malware by its anti-malware. That's what I've been marketed as. But I know there's a software out there that can give me this behavior analysis. Do I have to rebrand myself as EDR now, even though I'm doing anti-malware? My goal is still the same. I'm still just killing these viruses, worms, trojan, ransomware, and spyware. But maybe I'm not using that behavior analysis for data loss prevention and things like that. So I don't need to really categorize myself in EDR, but I can still take some of that technology and use it for my advantage, for what I actually do, what I actually market, what I sell in my niche, my expertise. And I'm talking about it like I'm the software, you know, but that's, so yes, the lines get a little blurred, but the key thing here is it prevents against this, guys: viruses, worms, Trojan, ransomware, and spyware. And how it finds those, it can borrow from these other technologies and still be labeled anti-malware. So it can still do this heuristic analysis, this behavior baseline that a SIEM does, that an EDR does. But guess what? An EDR is doing a lot more. It could be doing DLP, it could be doing HBSS functions, it could be doing a lot more, while this anti-malware is like, no, I'm gonna use these techniques to do exactly what I was made for. Stop those malwares, or stop that malicious software. Okay, Linux. So we've heard of group policy and Active Directory, Windows domain services, but what is the Linux version? What does Linux do? So Linux has something called Security Enhanced Linux, or SE Linux. It is a security mechanism used I like that, primarily on Linux systems. No shit. It enforces mandatory access control, meaning that system-wide security policies determine what actions, processes are allowed to perform. Break that down. Security Enhanced Linux. Everything on Linux is a process and it's a service. You know, when you get a Windows computer, the question is, what do I disable? You get a Linux device, it's, holy shit, I got a lot to enable. And everything you enable is some sort of service, some sort of process under the system's control, or like system D. So Security Enhanced Linux says, let me have some sort of mechanism to enforce, hey, you can't access this, or you can't access this file. You know, it's a file hierarchy system or standard. So, you know, it's built for Linux. So unlike traditional permission models where file owners control access, SE Linux policies restrict actions even for processes running with elevated privileges. So a good example, a web server process may be allowed to read web content files, but prevented from accessing system configuration files or databases, which that'd be hard, right? If the web server, if we're serving customers, we can't access the database. Well, maybe we just allow it to access the back end, right? So that's SE Linux. If you ever build a RHEL box, like, you know, in the DoD, RHEL is just widely used because it's already so hardened and the tools come easy. So like you can use SCAP to harden it. And then there's the STIGs. There's so much information online on how to STIG it and put it in part of your ATO. And, you know, if you guys, are any of you, in the chat, just raise your thumb. Are any of you guys cyber? Are any of you guys ISSOs or ISSCs? If not, cool. You don't have to raise your thumb. But, you know, that's what the ACAS servers run on. It's RHEL, then Nessus, and then Tenable. And that's our ACAS scans. So, anyways, it's very common. They enforce that. Okay, host-based firewall. Guess what? It's going to have a similar function as a firewall, but it's on the host. So it's just literally living on our endpoint. Browser isolation. This one's pretty cool. So this is pretty much allowing you to browse the web, browse the internet, go to different websites and web servers, whatever, right, web applications. But instead of running Google Chrome using your computer's own resources, your own RAM, your own CPU, your own network, we're going to open up a browser in some sort of cloud somewhere. So we're going to access a cloud portal and run a cloud web browser from there on a public IP that's maybe 1,000 miles away. So browser isolation is a security technique that separates web browsing activity from the endpoint's operating system, which again, you still got to access that cloud console portal somehow, and your operating system will do that for you. So obviously you can't completely break that chain, but what you're browsing, what you download goes to that cloud portal. And then if you want to like transfer a file, it's like a transfer process. So it's like, it's just protecting you from like clicking malicious links, things like that. Okay, configuration management. So in configuration management is the process of defining, enforcing, documenting, maintaining secure system configurations throughout the lifecycle of endpoints and servers. We do this with Git. So we use GitLab to maintain a golden baseline. And this helps us prevent against configuration drift and like, so for example, we have another customer. Our customers are GS employees. We don't actually work with like green suiters. So our GS employees like, hey, you know, I want all the ACL names the same. So instead of us like just opening up a notepad and being like, okay, let's redo our config on these routers and switches, what we do is we put everything in a Git repo, source control management. We make a master branch. Me and my coworker make, you know, we branch off that like a staging branch or whatever we call it. We go make those changes. We merge that to the master branch. And then that master branch has every single site for us, run a router and switch running config with all those changes. And then there's our new golden baseline that we go and install it on, that we use to then configure our routers and switches on. So that's configuration management at a very small scale. There's a lot of better ways to do it. There's a lot of third-party apps that allow you to do this. But that's kind of the basis of it, is like you don't want silos. Okay, MDM technologies, mobile device management. This is technologies that allow you to protect your mobile devices. It allows you to lock them out, do remote wipe, full disk encryption. It gives you its own app store. It can enforce a lot of security policies on your cell phones. Okay, TTPs. So threat actor tactics, techniques, and procedures. Just different ways they can attack our endpoints. So injection attacks, we have SQL, LDAP injection, XML injection. Now we have like AI chat prompt injection. So injection attacks occurs when attackers insert malicious input into applications that do not properly validate or sanitize user input. So how do we mitigate an injection attack, guys? With something called input validation. Input validation or parameterized queries, which pretty much says that if we're on a website and we're asking a user in question, we say, hey, user, what is your birth date? So instead of letting them type that in themselves, a parameterized query is a drop-down. Now, if we do let users put a lot of input into our websites, that's where they can do these injection attacks, where they put SQL code, or they do some sort of cross-site scripting or HTML code that's trying to get them to access the back end, right, with some sort of malicious code they're putting in the front end into an input field. To prevent that, we can do something called input validation, where built into the logic of the front end, we can say, hey, no, these input fields are only going to accept A through Z, lowercase, uppercase, and numbers. And so you can't do the brackets and all the special characters you need to run that malicious code. So when you try, our input validation is just going to stop it right there. It's not even going to let it go to our back end. Okay, privilege escalation. So privilege escalation occurs when attackers gain higher levels of access than originally authorized. This allows them to move from standard user permissions to administrative or root level access. Credential dumping. So credential dumping involves extracting authentication credentials from a system, often from memory or the operating system. This technique is especially dangerous because it enables lateral movement and persistence. Attacks using stolen credentials often appear as legitimate activity, making detection more difficult. So yeah, that's getting a system to dump some sort of elevated privileges, and then we use it. It's like, oh, this admin's just checking on this printer. Well, no, we were on that printer to create some sort of persistence or backdoor because it's made easier on the printer because it's not as monitored, and maybe doing data exfiltration from there may be easier. Unauthorized execution. So unauthorized execution occurs when attackers are able to run code on a system without proper authorization. This may involve executing malware, scripts, or built-in system tools for malicious purposes. So attackers often achieve unauthorized execution through phishing, malicious downloads, or exploitation of vulnerabilities. Preventing unauthorized execution requires controls such as application allow listing or whitelisting, endpoint monitoring, and restrictive execution policies. Okay, lateral movement. This one is just, part of almost like if you're doing like a penetration test, this is part of it, and that's just simulating a hack. So part of hacking is I exploit a system, awesome, but I don't want to stay there. I want to be able to jump networks, to get into maybe more sensitive networks, and just go around and make my footprint known at a bunch of different places. Now the problem with this though, what's the problem from the hacker's perspective of this? If you're jumping to all these places and you jump to a really monitored and secure server that may be taking, extra care and attention to, that could then, screw you over because now you're going to be caught. So lateral movement's supposed to be done very precise if you've done your reconnaissance and footprinting correctly. And how do we stop it? We stop it with network segmentation, monitoring for any abnormal access patterns between systems. That's where our AI large learning models come into play, where we create that user baseline. And then when something deviates from there, we're like, whoa, why is this credential or this user or service account that's in our data VLAN going to the printer VLAN from that host? Like, it may not just make sense. And we can have systems that can alert us to that. Okay, defensive evasion. So defensive evasion includes techniques used by attackers to avoid detection and bypass security controls. This may involve disabling security software, altering logs, encrypting payloads, or using trusted system tools to blend in with normal activity. So attackers may also use timing techniques, foul as malware, or obfuscation to reduce their visibility. So defending against evasion requires layered security controls, behavioral detection, protected logging, and continuous monitoring. Okay, let's go ahead and do our quiz. Okay, let's do our domain 3.2.1 quiz. All right, 3.3.1 after this. Okay, 4 questions here. Let's do this. All right, so question 1. Let me write this out on my other screen. An organization discovers that several endpoints have security features disabled and unnecessary services running, even though the systems were originally deployed using a secure baseline. So that's like we made a secure baseline and then we feel safe, but then it's like, well, we still got to monitor, right? Which security practice is most effective at preventing this type of issue over time? So just because we have that secure baseline, that golden standard, doesn't mean we stop and we're like, we're done. They used it. We're good now. So we need good management, good monitoring. So let's go ahead and look at our options here. So we have A, anti-malware signature updates. That's not going to prevent that behavior, right? Browser isolation, we love that. We love browser isolation. That's not going to fix this behavior. Configuration management is probably going to be our answer because D, host-based firewall rules, doesn't prevent this at all. So yes, configuration management. Awesome. Let's continue. So question 2. Let me write this out on my other screen. During an incident investigation, a security team finds that an attacker used stolen credentials from one compromised system to access multiple other systems across the network. Which threat actor technique does this behavior most closely represent? So they're moving around, stolen credentials, going to other systems. Yeah, that's an easy. That's a gimme, right? Let's not even go through the answers. That's lateral movement. So it's not an injection attack. Maybe we use an injection attack maybe to get them to download a malicious payload, do like cross-site scripting, and then, boom, we're in there. Now our malware is in there, and we can do a command and control service between them and get them to do lateral movement, whatever. But sorry, I need to cool it on the tangents. It's lateral movement because system to system, right? Easy. All right, question 3. A company allows employees to access corporate email and internal applications from their personal smartphones. The security team wants to ensure that lost or stolen devices do not expose sensitive company data. Which technology best addresses this requirement? So phones, mobile, personal smartphones. What are we going to do here? Yeah, MDM, right? You don't. If I just put the acronym, maybe it would be hard for us to tell. But yeah, mobile device management. So hard to do that on a personal smartphone. Now, I know some companies do. I guess I've heard of them doing it, but I wouldn't want my company installing nothing on my smartphone. But obviously, I have Outlook on my phone for the company I work for. So I guess I would. But I wouldn't want a full MDM solution on there that can lock down my phone. Now, sometimes companies will do this on Android because they can kind of sandbox it and almost put an OS within an OS, almost like a virtual machine that's really separate. So maybe I'd be fine with that because they say that it can't read the rest of the phone. But anyways, yeah, A, mobile device management. Good job, guys. One sec. Let's see here. Okay, question 4. A company wants to reduce the risk of malware executing on its database servers. These servers rarely change and only run on a small number of approved applications. Which security control would be most effective at preventing unauthorized software from running on these systems? So how do we prevent application installation? So a lot of times you'll hear this at the whitelist, the allow list, whatever, but it's application control here. So that's going to be B, application control. All right, awesome. So another 100%. Let's keep going, guys. Let's try to get through domain 3.1. Okay, now moving on to domain 3.3.1. Given a scenario, troubleshoot complex network infrastructure security issues. We're going to go over network misconfigurations, IPS, IDS issues, and DNS security. So here's everything we're going to go over. Okay, so network misconfiguration, configuration drift. It's kind of what I just talked about where, our routers and switches, our Palo Alto firewalls, they all have a configuration. Even though we're all doing SDN, software-defined networking, and SD-WAN, there's still, at the end of the day, is some sort of like configuration text file. There's just going to be. So what's configuration drift? That's where we build our golden baseline that says all of our sites, all of our switches, all of our routers are going to have these things. Then over time, depending if we're a global enterprise, we may have a tier 2, tier 3 admin over here change something over here. It's configuration drift. They add a permit statement to this site because they had something unique going on with the user, and now the other sites don't have it. So now if someone comes on board, they're like, this isn't on part of the baseline. You're like, yeah, well, we needed this. Hey, Kevin, do you remember why we needed this? That's always those conversations. Like, why did we put that there again? So that's kind of the problem with configuration drift is when we don't have the documentation to then say, hey, this little Jinja template that we made for site 1 is going to differ from all the other sites. And let's document that. Let's put it in its README or whatever kind of Git source control management you have. Maybe you have another way to do it. And so we can have, prosperity of that. Okay, routing errors. So how does a senior network engineer talk about routing errors in one slide? When your traffic isn't being forwarded correctly, as a cybersecurity professional, there may be some routing errors that you may have to be involved in. I don't really know when a cybersecurity engineer would get into, a router CLI and do this, but just know that it is there and maybe affecting your system. So maybe that's why they want you to know about it. Like, hey, maybe your scanner isn't updating and replicating the right way. And the network team says, yeah, we have some asynchronous routing going on here. So, atomic timing, synchronization of your database or your storage or whatever your case is not going to be perfect right now until we fix this asynchronous routing, which is kind of what I drew up here. So let's see this. Routing loops can cause traffic to circulate, unnecessarily increasing exposure and interfering with monitoring tools. Yeah, I guess that's true. We'll move on. Okay, switching errors. So again, what I think of if I'm a cybersecurity professional and I'm looking at a switch, I'm really looking at the layer 2 security. I'm worried about MAC flooding attacks. I'm worried about ARP poisoning, DHCP poisoning. But there are switching errors that like STP can mess up. We can assign incorrect VLANs. We could build isolation or private VLANs to isolate something that got exploited. We could have trunk configuration errors. We could have port security on the switch. We could have MAC authentication bypass. We could have a MAB on there to help us with 802.1x. Kind of an old school way to do it if you don't have certificates on the computer. So port security is MAC address filtering. Yeah, I see that. Okay, spanning tree, right? So of course there's spanning tree issues, but is that really a cybersecurity function? That's why I'm why did they talk about this? Because if there's a spanning tree issue, it's everyone's problem. Because if there's a broadcast storm, all those switches aren't forwarding traffic correctly. If there's the improper root bridge of spanning tree, okay, there's an improper root bridge and the network team has to figure it out, but eventually it'll route, it'll get out, But yeah, spanning tree issues. But is it a topology change, right? Because if, let's say switch 1 here should be the root bridge, right? Let me bring my pen out. Switch 1 should be the root bridge. Because switch 2 down here is connected to more access switches or whatever and more users. But let's say switch 3 here becomes the root bridge, becomes the king of the castle, right? And then it's connected to the router here. And so when I have a user over here and I need to send to the router, what comes first, right? Layer 2. So it's going to be a part of VLAN 10. And VLAN 10 is going to say my root bridge equals switch 3. So it's going to send its packet here. And then this switch is going to say, okay, this frame is destined to our default gateway because the destination MAC address header field is heading to the default gateway. So I need to send it here. And then this switch sends it here. Now, that's not efficient, right? That's not efficient. But what's the problem there? Now, I will say if there's spanning tree issues that are something like this, Well, suboptimal, yes, but like it's cyber. That's a cyber issue. Probably not. It's more like a network configuration error and issue that really wouldn't affect your attack surface. It really wouldn't affect like anything expanding. There's nothing that a hacker could, exploit. So if you're adding in a switch from like the comms closet that doesn't have the proper security on it anyways, if it becomes a spanning tree root bridge, that's really not going to change that increase your attack surface. So if an authorized switch took over, yes. So like root guard could be enabled. If you don't have root guard, yeah, like a switch could take over that's not authorized. But again, that's more like the network team, not really like cybersecurity. That's just like the basic network, hardening things, which a cybersecurity professional could be like, yeah, I just need to make sure you're doing these things. It could be part of the hardening devices. But if there's a spanning tree loop, the cybersecurity team is really not going to be taking on that task. That's going to be, the network team. So, yeah, we have to be aware of switching errors. We have to be aware of how to harden switches as a cybersecurity professional and what they do. More or less not like, okay, this is happening real time, right? Like, let's start troubleshooting. That's what the STIGs are. When we do like switching STIGs, like on there, if you ever looked at a STIG with your ISSC, it says, is root guard enabled? Is BPDU guard enabled? Is spanning tree port fast enabled on only user ports? Are all these things enabled? And that ISSC pretty much just understands, like, I need this to harden, but if there's a spanning tree issue, it's going straight to the network team, But yes, we have to be aware of these things, but it's not necessarily part of our, like, daily duties as an ISSO or ISSE or cybersecurity analyst to say, yeah, let's go fix that spanning tree issue. If there was, like, a loop in the network. Which could happen, yeah. If someone grabs a switch from, like, a comms closet and just plugs that thing in, it could definitely take over. That could be set to like 0. Okay, hold on. Let me close this. Okay, insecure routing. So this one, could open us up to a man-in-the-middle attack saying, hey, if we don't have like our routing protocols doing some sort of authentication, it could introduce a new router into the network that may be unauthorized, especially if you're in like a shared Ethernet space. So insecure routing refers to routing configurations that function correctly from an operational standpoint but lack appropriate security protections. We're going through this right now. Let me pull the chat up again in case you guys have more discussion because I do like that. What was I talking about? So, OSPF, for example. OSPF has an authentication field that has to match between all of its OSPF neighbors. So that authentication field is just literally a password or what we call a key, but it's really just a password. And that sends over plain text by default. But you can set up a hashing algorithm like MD5 or like CMAC, AES, or like SHA-256, SHA-512 to take that plain text password, create a hash, and then insert that hash into the packet that again gets sent across the wire. So if there's someone sniffing in the middle, then they'll just see a hash. They'll just see a bunch of digits, a bunch of hexadecimal digits. They can't crack that. That's the hope. But what's the problem with one of those hashing algorithms I talked about? The problem is, like if you use MD5, that's insecure. That is like insecure and vulnerable to what we call collision attacks. So we just got to make sure we're using the best authentication protection mechanisms. Or like in big BGP networks, like sometimes we'll authenticate using what's called like a tag, like a BGP tag. So it's like kind of like if-then logic. So we'll like create a route map and apply that route map to BGP that says, hey, if you get tag 10 from this autonomous system neighbor, then insert into this BGP table, the adjacency BGP in an outbound table, and then push that up to the global routing table. But I've never seen anyone do that honestly in practice. I've seen tags be used for routing, but not like for like authentication, but that's another way. Okay, VPN and tunnel errors. So virtual private networks and tunneling technologies are used to protect traffic as it traverses untrusted networks, but they introduce additional complexity. So VPN and tunnel errors often result from mismatched configurations, incorrect encryption parameters, or failures in authentication. So let's just talk, it's easy to break this down. We talk like IPsec, right? So IPsec has two modes, tunnel mode and transport mode. And each time you do IPsec, let's say we're using Internet Key Exchange like V2, we have like a proposal, we have a keychain, we have an IPv2 profile, and then we have an IPsec profile. And within all these things, you know, the proposal, I'm missing one. I can't think of it off the top of my head, one before the proposal. But if we look at the proposal and then, you know, the keys and then the IPv2 profile, from one router to a firewall, router to router, those things have to match. The hashing you're using, the encryption you're using, the authentication you're going to use, whether it's going to be a certificate or a password, and the encryption type you're going to use all has to match. So in VPNs, when you're building a VPN, you have to make sure that pretty much whether you're doing Palo Alto to Cisco ASA or Cisco Firewall, you just have to line it up. Like we're introducing Palo Altos into our out-of-band management network at my day job. And so we're in our system integrations lab. We're putting in one Palo Alto at a site per time. So right now we have one Palo Alto in there connecting to a Cisco ASA pretty much shop, you know, domain with like 4 sites on ASA. And then we have this one site on Palo Alto. And when we built the IPsec tunnels, we literally just looked at the ASA code and said, okay, here's the group we're using. Here's the secure key exchange, the encryption. Now we just have to pretty much translate that to this Palo Alto GUI and make sure all those matches, because it's still a process, you know, proposal, key, IPv2 profile, assign that to an IPsec profile, and then assign that to like a tunnel interface, you know? So it's all the same, even like cross vendors. Okay, IPS, IDS issues, rule misconfigurations. So a rule misconfiguration is the same whether it's IPS, IDS, a firewall, anywhere, right? So rule misconfigurations occur when detection or prevention rules are improperly written, outdated, or poorly tuned for the environment. A rule that is too specific may miss variations of an attack, while a rule that is too broad may flag legitimate activity as malicious. This is always like how, you know, when you fine tune your systems too much, it's like everything's a problem, you know? We're gonna generate all these flags and all these alerts, and it's gonna just bog us down, and then we could miss something in the noise that maybe was legitimate. But then if we're too relaxed, if we're not if we're not, you know, fine-tuned enough, maybe we actually just do miss things that we don't get alerted. So you got to find that nice middle ground when it comes to like IPS, IDS, logging, and alerting solutions. Some more other issues: lack of rules, false positives, and negatives. So an IDS or IPS cannot detect threats if it's not configured to recognize those threats. So systems deployed with default or outdated rule sets may provide minimal protection. So imagine you just, you know, you're on your Palo Alto, you just enable IPS, and it's just like the default library or something that says, do this IPS rule matching. You know, that may not be well configured for your environment, because maybe that default one is just for like what they consider a regular enterprise, but maybe you're in an OT environment. Maybe you're in like my environment, we mess with full motion video. So we don't have traditional users that are like always accessing Office 365, all these enterprise applications. It's video streams, which is like multicast and a host of other things that common IPS, IDS library may not contain. So false positives occur when legitimate activity is incorrectly flagged as malicious. False negatives occur when malicious activity goes undetected. Both undermine confidence in our detection systems, but false negatives pose the greatest risk because attacks continue unnoticed, right? False positives are more like annoying. It's more like, okay, we're wasting some time here when we could be doing maybe better threat hunting capabilities and blue team activities. But false negatives is like horrible. That means your system's pretty much, in my mind, not inoperable, but it's not operating as it should. It's not detecting or preventing the actual thing it should. In my opinion, I'd rather have a system that's maybe a little bit noisier than missing something if I'm in a cybersecurity focused enterprise. Oops, sorry about that. Placement and observability. So the physical or logical placement of IDS and IPS components within the network is critical. Poor placement can result in limited visibility or complete blind spots. So like, you know, you put that sensor, let's say it's an actual sensor that's in line somewhere. We have those on these taps that we have that's like sending out to our DISA, our big DISA overlords, like so they can monitor our traffic that's connected right to their MPLS cloud. Anyways, with that placement, it kind of sits out of the way because we don't want it inline and disrupting traffic. But what may that do? Even though we're spanning it, even though we're spanning a switch port that's spanning from the data port that connects to our firewall, which is our outbound perimeter like routing device, maybe we might miss something in that tap. But if we do it in line that says, no, capture everything, then it's probably going to capture everything. But then what are we prone to? User traffic going down. That, you know, it introduces an extra troubleshooting step where a user can't reach something. So we go into the router. We're like, well, if I'm sourcing this from the router, I can reach it. So then you're like, okay, let's go check our IDS, our IPS system. Let's see if it's blocking it from this specific user IP, you know? Okay, DNS security. So DNS, we didn't really, you know, again, this is a professional level cert, so the expectation is you know what DNS is, you know, IP to name resolution. As much as I love to deep dive into DNS and how global DNS works, and there's like 13 major providers, and we can get into recursive server, you know, the canonical name, whatever, you know, we're not going to. We're just going to talk about how DNS needs to be protected because it's inherently insecure. You know, it operates on UDP port 53. It can be TCP too, and it's open. You know, so how we protect DNS, so we usually want to hide it, or not hide it, but use it inside of HTTPS or add TLS to it. But beyond that, DNS really doesn't have any authentication built into it. So it's like if I just want to reach out to a DNS server that's public, I can just use it. I don't need to trust it. I don't need to look to see if there's like a certificate associated with it that says like, hey, I got this issued by a trusted root CA, so your web browser should trust me when doing DNS resolution. You know, we don't have that. And since it's something that we need to browse the internet, we have something local. We also fall victim to like man-in-the-middle attacks where we get maybe our DNS requests redirected. Maybe someone gets in our DNS server and puts bad A records in there that are actually doing the IP to name resolution. So DNSSEC protects. So DNSSEC is a protection mechanism. It protects DNS integrity by allowing resolvers. That's like the first hop in your DNS. That's something that may be local. If you do IP config all on your computers and maybe your default gateway, that's your DNS resolver, which is like your ISP technically. Moving on. By allowing resolvers to cryptographically validate DNS responses. So what this uses actually is like PKI, guys. Essentially, it says like, hey, we're going to add this security extension onto my DNS packet request. And when I go to my DNS server that I'm configured for, I need to authenticate with it first and trust its certificate. And we start building this chain of trust and this validation. So misconfigured DNSSEC can lead to resolution failures or leave systems vulnerable to spoofed responses. Okay, DNS poisoning. DNS poisoning occurs when an attacker inserts false DNS information into a resolver's cache, redirecting users to malicious destinations. This often results from weak access controls, lack of DNSSEC, or vulnerable DNS software. So how do we troubleshoot that? Check out your DNS servers and make sure there's no bad records in there. Okay, sinkholing and zone transfers. This sinkholing is something new I actually learned when building this course. So sinkholing is a defensive technique that redirects malicious or suspicious traffic to a controlled destination. While effective, misconfigured sinkholes can disrupt legitimate services or obscure network visibility. So this is just like configuring something in a DNS server that I've never personally done before that says, hey, let's inspect where we're getting these requests from. Let's look at maybe their source IP, and if it's from a well-known blacklisted domain, we're not going to accept it. So we're going to send it somewhere else to get logged and trafficked. Now, obviously, what's the problem with that? If, again, you're super strict, it's misconfigured, it could maybe a legitimate user that you do that to. Okay, zone transfers. Zone transfers allow DNS servers to replicate zone data between authorized servers, and if improperly secured, attackers can retrieve entire zone files and gain insight into internal systems and network structures. Then we have unauthorized zone transfers, which is super hard because I've done zone transfers. Like I've bought a domain under like, what was it called? Bluehost. And I had to transfer it to my Google domain that I wanted to put it under. So I pretty much had to say, hey, new authorized like domain name resolvers I want to use. I want to transfer it to my Google domain services. And it was only like available for like 7 days. I needed an API key that was only available to my Bluehost panel that I had to like log in, multi-factor authentication in. So technically, I guess they unlocked it for me so I could do that zone transfer, that Bluehost. But if an attacker knew that at the time, could get in and get that key, they could have transferred it to themselves. Okay, let's go ahead and do this quiz and then we'll take a break. I don't think we've taken a break yet. Have we? No, okay. Yeah, we're cooking because I want to finish domain 3 for you guys. So I'm like, trying to go a little bit faster by. All right, let me just get set up over here on my other screen, guys. Bring the chat up. Question 1. A security administrator discovers that internal DNS queries are intermittently resolving to malicious IP addresses, even though the authoritative DNS records have not been changed. Restarting the DNS resolver temporarily fixes the issue, but the problem returns after several hours. So pretty much that resolver is getting that bad shit again. What is the most likely cause of this behavior? So our resolver is the one that sits on network with us. It's our first hop in the DNS resolution scheme and like data flow. So let's look at these answers here. A, unauthorized zone transfers are exposing DNS records to attackers. No. DNS sec validation failures are preventing legitimate DNS responses. No, nothing to do with authentication there. DNS cache poisoning is inserting fraudulent records into the resolver. D, synchrolling is redirecting traffic for analysis by security tools. That could have been it, right? But I think C is the most likely answer here. That's going to be DNS cache poisoning is inserting fraudulent records into the resolver. Yeah. Keeps going back, so it must be the cache. Yeah. Oh, yeah, that's true, right? Yeah. Yeah, the restart. Because if it was synchrolling, it would have done it immediately. Yeah, true. Very true. Question 2. During a security audit, an organization discovers that its network routing is functioning correctly, but routing updates are accepted from neighboring devices without any formal authentication. The organization is concerned that an attacker could manipulate traffic paths without triggering intrusion detection alerts. Why is this routing configuration considered a security risk? Okay, maybe I missed it on one of the slides. I think I wrote it down there. But if this happens, like let's say you're doing OSPF and you forgot to type in the command passive interface, so then OSPF hello packets are going downstream. And some very savvy hacker says, you know what, let me open up a virtual router on my on my VMware player, and I'm gonna become fucking routing neighbors with them because I'm gonna do, the command OSPF router neighbor and like make it a TCP connection almost, right? It's not, but you direct it. It doesn't have to be directly connected. So they become OSPF neighbors, and now all of a sudden they can start injecting crazy things to the routing table that, send it to nowhere. It's like black hole. So that's really the problem here. If that happens, it takes a lot for that to happen. And I don't think anyone's infiltrating ISPs lately. Who knows? Verizon just went down. Who knows if that was misconfiguration, hack, whatever. A lot going on in the world right now. But if a attacker is able to become part of that routing domain, yeah, it's going to inject bad routes that could lead to users not being able to access. Something like a denial of service attack, right? So I'm going to go with D. It allows attackers to inject false routes and redirect traffic. Okay, question 3. Let me type it in over here. An organization deploys an intrusion detection system to monitor traffic entering its internal network from a remote branch office. The IDS is placed on the perimeter firewall interface facing the internet. The branch office connects to headquarters using a site-to-site VPN. Despite confirmed malicious activity occurring at the branch office, no alerts are generated by the IDS. Whoa, they didn't tune that good. What is the most likely reason the IDS is failing to detect the malicious activity? All right. Let's read this again. Organization deploys to monitor traffic entering its internal network from a remote branch office on the perimeter firewall interface facing the internet. Site-to-site VPN. No alerts are generated. Okay, there's no alerts being generated for that malicious activity. So it can't be the false positives because it just doesn't say that. It doesn't say anything about tuning. I think this is trying to get us to talk about placement here just because it literally says IDS is placed and it's like, but it's failing to detect. So I don't think it's going to be a tuning issue actually. It lacks sufficient processing power to analyze traffic at line speed. There'd be no point to build an IDS that couldn't do that, so that's not it. The IDS rule set is outdated and does not include signatures for the attack. I mean, I guess that could be it. Despite confirmed malicious activity occurring in the brand, no alerts are generated by the IDS. But that'd be, I don't know. I think it's getting us to talk about placement here because it is place. So yeah, I'm gonna put B. The IDS is place where it only sees encrypted VPN traffic. Where did it say place on the perimeter firewall and there's a site-to-site VPN? I kind of don't like this question because it makes us assume a lot of things, like that the site-to-site VPN is living at that firewall. It didn't really tell us that though. And that's not always the case. Like routers can do site-to-site VPNs and that firewall could sit outside of that and it could just be doing monitoring. It could be doing packet inspection, who knows? That'd be a bad thing, but it's B. I think it's B because it's talking about placement. I think the place is the key word. So the explanation says, the intrusion detection system is positioned on the external interface of the firewall. Did it say that? Facing the internet. Okay, yeah, it did. Which means it is observing traffic before the VPN tunnel is decrypted. Yeah, makes sense. And it's not doing decryption because who knows if it's IPsec. Maybe it can't do IPsec decryption, that IDS. Yeah, okay, makes sense. All right, let's go, 100%. Okay, we're going to take a break. I just want to see how much we got left here. Domain 3. So we got to get through 1, 2, 3, 4, 5, 6, 7, 8. 8 slides. All right, I'm going to try to do I'm going to try to get us, yeah, we should be good. Only 8 slides. Do 3 slides at a time, take a break. Yeah. Okay, guys, let's go ahead and take 10. And then when we come back, we'll continue on. We'll finish up domain 3.3. Okay, guys, let's go ahead and get started again. Let's go ahead and finish up domain 3.3, given a scenario, troubleshoot complex network infrastructure security issues. Now we're going to go over security issues, email security issues, and encryption issues. Okay, so here in the red is what we're going to go over. And it's so funny, network access control list issues. We kind of already went over some of this stuff, like PKI issues with cryptographic, but again, that's okay. We repeat a little bit in CompTIA. All right, starting off, let's go over some email securities. We're going to go over SPF, DKIM, and then DMARC, SPF, DMARC, and DKIM. It's usually how it goes. So SPF, the Sender Policy Framework, this is actually going to be like really text that you put into your DNS records or into an actual like email gateway to protect your DNS and your actual email domain. So, is an email authentication mechanism designed to prevent sender address spoofing. So SPF works by using DNS records. A domain owner publishes an SPF record that lists the mail servers authorized to send email for that domain. When a receiving mail server gets an email claiming to be from a particular domain, it checks the SPF record for that domain and verifies whether the sender server's IP address is on the approved list. So really what we're saying here, like when I first started the Trepa Tech domain, we had our SPF records all messed up on our Bluehost DNS records. It was an us issue. They didn't make it really easy for you. And because we were using like Google Suite, it was like, we use Gmail, but it's like G Suite Business. Some people were just going straight to spam. So we had to put SPF records into our DNS, and it pretty much said, hey, we're not spam. We're actually like a legit company. And still, really, you can't prevent it because sometimes spam isn't even to do with, spam filtering isn't to do with like the sender email server IP address. It's more or less just like, oh, like that text in this email is like marketing. So, but that's kind of the nice thing about having a G Suite and you have a Google domain and that hosts it. And it's on Squarespace now though. It's Gmail, so like the SPF record coming out of there is Gmail, which is trusted in a lot of places. But if the sending server is not authorized, the SPF check fails. An SPF failure does not automatically mean the message is rejected. Instead, it provides information that the receiving system can use when making a delivery decision. Again, like us going straight into the junk mail. Okay, DKIM. So DKIM focuses on message integrity rather than message origin. While SPF verifies where an email comes from, DKIM verifies whether the message was altered after it was sent. So with DKIM, outgoing email is digitally signed using a private key held by the sending domain. So digital signatures actually use asymmetric encryption, but we kind of do it opposite in the way we encrypt. I taught you in PKI that, the public-private key pairs can encrypt and decrypt. So when we're using asymmetric encryption like the TLS cipher, we grab the receiver's public key, and we encrypt our message. And then when the message goes to the receiver, only its private key can decrypt. With digital signatures, it's different. We encrypt the digital signature with the server's private key. So if I encrypt with my private key, and I'm the server, and I send it out, now you're the receiver, what's the only thing that can decrypt that message? If I encrypted with the private key, the relationship between the public key is that it decrypts and vice versa. So if I encrypted the private key and I send it on my digital signature, you're doing a DKIM check, you take my server's domain name, like trepatech.com, you take my public key and you try to decrypt and it works, then yes, it was sent from Trepa. If it doesn't work, it was altered. Something was messed up. So that is how DKIM works and how, the digital signatures actually prove authenticity, non-repudiation, and integrity. Okay, now DMARC, domain, you ready? Domain-based message authentication, reporting, and conformance. So DMARC builds on both of these technologies. So DMARC builds on SPF and DKIM by adding enforcement and reporting. While SPF and DKIM simply pass or fail, DMARC tells receiving systems what action to take when authentication fails. So a DMARC policy can instruct receivers to take no action, quarantine the message, or reject it outright. DMARC also introduces alignment, which ensures that the authenticated domain matches the visible sender address shown to users. Okay, SMIME, Secure/Multipurpose Internet Mail Extensions. So SMIME provides encryptions and digital signatures at the individual message level rather than just the entire domain or the entire server. SMIME is like, hey, this is coming from this specific user, so that user may digitally sign this, not necessarily the server. So SMIME gives you that per message level encryption and authenticity and non-repudiation with the digital signatures. Usually just put on there as an extension. Okay, TLS errors. Let's talk about transport layer security. We actually deep dived into it in PKI. We said TLS cipher suites are built off asymmetric encryption, secure key exchange, and symmetric encryption. And that's your TLS cipher suite. Now, what could be the problem when you're a client to a server, you're establishing the HTTPS session, and you're doing that TLS handshake? If there's a man in the middle, you can't have a weak stream cipher like RC4, a weak encryption period, and that's, a lot of the errors. You may have a mismatch and one is only accepting TLS 1.3 and it's not downgrading to what you can send at TLS 1.1. So TLS errors occur when a secure session cannot be established or maintained. These failures may result in service outages, connection warnings, or silent communication failures depending on the application. Common causes of TLS errors include protocol version mismatches, certificate validation failures, unsupported encryption algorithms, and misconfigured trust stores. So again, just dealing with PKI, that trust, that chain of trust, the certificate authorities, and then what I just talked about, like mismatched versions or weak ciphers. Oh, there we go, cipher mismatch. So let's talk about that. Because a cipher mismatch just doesn't have to be TLS. It could be in like IPsec even. So a cipher mismatch occurs when two systems attempting to communicate securely cannot agree on a shared encryption algorithm. During the initial handshake process, each system presents a list of cryptographic ciphers it supports. If there is no overlap between these lists, the secure connection fails. So imagine, actually I don't have to imagine. In my environment we work in, without giving too much away, we have these console servers that cannot upgrade their TLS. They literally can't. Because one, they have an immutable freaking file object that we can't adjust. That's like the SSL cipher file, .cnf file, that tells you exactly what cipher suites to use, and it will not let us get rid of the MD5 RC4 one. Not MD5, it won't let us get rid of the RC4 one, so it keeps coming up on our scanners as like a vulnerability, right? And so it's weak. So it will allow like that downgrade attack because we cannot literally get rid of that RC4 stream. And if we have advanced web browsers that have like TLS 1.3, obviously they can always downgrade, but we can't hit it because we can't upgrade that TLS cipher suites either because it's a muted thing. Yes, we got with the vendor and they pretty much just told us like, hey, we no longer really, like, we support this product, but this is gonna have to go to our backend developers, and it's been 9 months now. So maybe we should follow up, but that's cipher mismatches. A key word there, legacy, right? I just saw it. Where'd it go? Cipher mismatches commonly occur when legacy systems attempt to connect to modern servers that have disabled older, weaker encryption algorithms, right? It does happen but really we're just gonna replace them, honestly, is what's gonna happen. Okay, PKI. So PKI issues, the public key infrastructure. The public key infrastructure is the foundation of trust for many security technologies, including TLS, SMIME, and digital signatures. PKI relies on certificate authorities, and trust chains to verify identity. If you missed our PKI section, guys, I got to upload these recordings for you guys, actually, so you can go back and watch if you want. PKI issues arise when a system cannot validate the authenticity of a certificate. This may occur due to expired certificates, certificates issued by untrusted authorities, missing intermediate certificates, or mismatched certificate names. We saw this where we were going to a DoD site via HTTPS, but we got that warning because it wasn't a trusted CA that signed it. Issues with cryptographic implementations. So not all cryptographic failures are caused by misconfiguration. Some result from how cryptographic algorithms are implemented in software or hardware. So implementation issues can include weak random number generation, improper key handling, like if you don't have key escrow, or maybe you're storing keys in a hardware security module that doesn't have enough compute process to actually store them, and maybe you do key escrow there and it's not properly doing it. Incorrect certificate validation logic, or insecure fallback mechanisms. Inconsistent cryptographic libraries across systems can also lead to unexpected behavior. These issues are particularly dangerous because systems may continue functioning while silently weakening security. Okay, DOS and distributed denial of service. So, SecurityX, like I said, we don't have to dive deep into all the different ways to do DDoS, where I tell you about bots and botnets and command and control servers, and we get into the ports, and I show you how to analyze that, and we get into the types they do when it's API, maybe it's a SYN flood, all these different types. That's in my CYSA class if you're interested. But this is high level. What are they? It's just any sort of attack coming from the network or coming from, we're just going to keep it there. Coming from the network that attacks a specific public service that tries to overwhelm it and then disrupt the flow of regular normal traffic and what should be regular authorized users. So denial of service attacks aim to disrupt the availability of systems rather than compromise the confidentiality or integrity. They just overwhelming the system with traffic or resource requests. In a distributed denial of service attack, traffic originates from many sources simultaneously. So essentially what we're saying here is like, in my garage, I could set up, let's say no, that'd be a lot. In my entire house, 1,000 Raspberry Pis. I don't know how much power that would draw. Let's say I'd set up 1,000 Raspberry Pis and I connect them all to my internet and we start doing SYN flood attacks. That's a denial of service attack. That is coming from one source IP. Pretty easy and obvious for advanced systems to say, I see what's happening here. That's coming from a single source IP. That's a denial of service attack. Distributed denial of service is when, again, it's like you have that botnet and you have all these zombies or bots all around the country, all around the world maybe, that you send a command and control message to, and then they activate, and then you conduct your attack, and they're coming from what looks like a lot of legitimate requests because they're from all over the place. Resource exhaustion. So resource exhaustion occurs when a system's finite resources are consumed faster than they can be replenished. This can be caused by malicious attacks, misconfiguration, or unexpected workload increases. Resources commonly targeted include, this is all like compute here, CPU, memory, disk I/O, it's like storage, but network bandwidth and connection tables. So the core functions of computing is compute, storage, and networking. That's what can be exhausted as a resource. Network access control list issues. So access control lists, we put them everywhere, and what could be the problem with that? It denies legitimate traffic. It's something I deal with all the time, honestly, in my day job. We just had one where we had to put a permit statement for a destination IP because we had one filtering based off destination, but we had a permit for the source, so we had an error there in our access control list on our layer 4 at ACLs. So troubleshooting ACLs is very important. You can go to logs. A lot of firewalls have logs that you can look at when looking at like ACL rules. And you just want to comb through your permit and deny statements and see what ports and protocols you may actually be denying that could be legitimate. All right, awesome. Let's go ahead and do our quiz now. All right, let me get set up on this other side here, guys. Okay, question 1 of our domain 3.3.2 quiz. A network administrator notices that a public-facing service becomes unresponsive during periods of high traffic. System monitoring shows CPU utilization at 100% and a rapidly increasing number of half-open connections. Looks like a SYN flood, right? Or let me see. No, we're talking CPU. Yeah, CPU utilization at 100% and rapidly increasing number of half-open connections. No configuration changes were made prior to the issue. Which type of security issue is the most likely cause? CPU, right? So that is going to be resource exhaustion. All right, yeah, we were right. I think we haven't missed a question yet, guys, so we're doing pretty good. Okay, question 2. An organization enables a strict email authentication policy that instructs receiving mail servers to reject messages that fail authentication checks. Shortly afterward, users report that legitimate emails sent from a third-party ticketing system are no longer being delivered. The email headers show that the SPF passes, but the messages are still being rejected. Which technology is most likely responsible for the rejection of these messages? Okay, so we have SPF passing. Our SPF checks are passing on our server, but the email header showed that SPF passes, but the messages are still being rejected. So it's dealing with servers because third-party ticketing system, that's probably like an external third party that we're integrating in, right? So it's probably going to be a different domain name. So it's not going to be D, ruling that out. SPF's good, so let's roll out A. So now really what we're looking at here is DKIM and DMARC. DMARC just verifies like the integrity, right? It does like the digital signature thing. DKIM, so I'm going to go with C here. Domain-based message authentication reporting and conformance. It's a fucking tongue twister. Let's read it. So this scenario describes a situation where email authentication checks are technically passing at one level, but messages are still being rejected due to policy enforcement. SPF passing alone only indicates that the sending server is authorized to send email for the domain. It does not determine how receiving servers should handle authentication failures or alignment issues. DMARC is the technology that ties SPF and DKIM together and applies enforcement rules. When a DMARC policy is set to reject, receiving servers are instructed to discard messages that fail authentication or alignment requirements. Even if SPF passes, DMARC can still fail if the authenticated domain does not align with the visible sender address or if DKIM fails. So pretty much we're saying that if SPF passes, that still doesn't mean that DKIM or DMARC passes. It's different pieces of the puzzle, total puzzle to email security. So we're going to say DMARC because here it's more than likely that it was, authentication. Then it says third-party systems frequently cause DMARC failures if they are not properly configured to align with the organization's domain, making DMARC the most likely cause of the rejection. Okay, cool. All right, question 3. A legacy client application fails to establish a secure connection to a newly hardened web server. The server logs indicate that the TLS handshake fails before certificate is exchanged. No certificate errors are reported, but the connection is terminated immediately. What is the most likely cause of this failure? So legacy, when we have legacy and we're doing TLS, what is probably always going to be the problem is that it doesn't have the right version, which all that means is that the ciphers aren't lining up. Because like TLS 1.1, 1.2, 1.3, like 1.3 has some enhancements called like ECH we don't have to get into here. But beyond that, it's just like stronger cipher suites. It's really all it is. So yeah, this is probably more than likely a cipher mismatch. Sweet, another 100%. Let's keep it going, guys. So now moving on from domain 3, now we're going to go over domain 3.4.1. Oh, there's a lot of slides. Okay. Given a scenario, implement hardware security technologies and techniques. Let's go over all these exam objectives here. Dang. Okay. So yeah, so now we'll be going over domain 3.4.1. Given a scenario, implement hardware security technologies and techniques. All right, so here's all the exam objectives we're going to go over. More threat actor TTPs. I feel like we covered this probably like 4 times already. That's okay. All right. Roots of trust or root of trust. So a root of trust is the foundational security component that is inherently trusted because it is designed to be secure and resistant to tampering. So what are we talking about here? Is that when we boot up our machine or our device, that from the OEM hardware that's in our motherboard, let's say from the computer standpoint, we should be able to trust every component on there and validate that every component has not been tampered with. That is our root of trust. So let's look at this. Root of trust typically performs 3 critical functions. First, they securely store cryptographic keys. Second, they securely measure system components and system state, pretty much saying, what are you at? Third, they securely report these measurements so other systems or administrators can verify the integrity. So that's like when we do secure boot. This is a form of root of trust where I kind of talked about it already, where you take your OEM hardware that's on the motherboard, you get a hash of it, which is like here, the cryptographic key, whatever, of the current state it's in upon first boot, put that in a TPM, a trusted platform module, and then the trusted platform module stores that, and then the next time you boot up, it's going to do that exact same process again, but now it's going to do the process. When it gets to step 3, it's going to take that hash that it created from the OEM doing its check and compare it to the original one. And if it's different, you're not going to boot. But if it's the same, nothing's been tampered with, so you're good to go. Okay, so TPM. A trusted platform module, commonly referred to as a TPM, is a dedicated microcontroller installed in the system motherboard or integrated directly into the CPU. Its primary purpose is to securely generate, store, and protect cryptographic keys. So unlike software-based key storage, a TPM isolates sensitive cryptographic material from the operating system. So even if we gain root access, this is why secure boot is nice, because let's say we get, root access to the device, a TPM is supposed to be secure still. So a TPM performs several important security functions. It generates encryption keys using hardware-based random number generators, which are more reliable than software-based randomness. It securely stores keys so they cannot be copied or exported. And it measures system components during the boot process and records those measurements for later verification. So beyond just what I like to describe, the example I like to use for TPMs, it can do more. It can, be part of the actual encryption and key generation. And as you see, since it's hardware-based, it's more random. Have you guys ever seen this before? Cloud, flare, lava, lamp, wall. Yeah, let's see. So like Cloudflare, they use these lava lamps and how the bubbles move to generate encryption keys, because they're like, this is so random, no one could ever mimic it. It's pretty cool. But that's like when they say randomness, like in software, it's kind of like hard to be totally random because it's like that logic, that computer logic, ones and zeros. But when it's hardware or something in the real world, something like that, it may be a little easier, maybe harder to crack because it is so random. It's harder to, mimic that randomness. It's pretty cool what they do there. Okay, HSM. A hardware security module, HSM, is a specialized hardware device designed specifically to manage, generate, store, and protect cryptographic keys at scale. So TPM is on a single computer. A HSM could be a total, like a 1U rack device that's used for like an enterprise or used in the cloud. So HSMs are often used for certificate authority operations, secure key management for encryption services, digital signing and verification, and payment processing systems. Okay, virtual TPM. Yeah, thanks, Jeremy. It is dope, right? I thought it was cool. I got a couple buddies actually from the Army that work at Cloudflare, and they fucking love it. They're like in the public sector part. But anyways, I don't want no more tangents. We got to get through this. A virtual trusted platform module, or vTPM, provides TPM-like functionality to virtual machines. Since virtual machines do not have direct access to physical hardware components, the virtual TPM is implemented through a combination of hypervisor controls and back-end hardware, such as the physical TPM or HSM. So it just gives our virtual machines have the ability to do things like BitLocker, to store their own keys for that virtual machine securely. So it's like, hey, if I have a virtual machine, I know it's using the underlying, physical hardware, but my hypervisor manages that. So imagine you're trying to say this virtual machine is secure, but really its attack surface could be that hypervisor. So it's kind of giving us a way to isolate what a TPM would do for a computer to a virtual machine or a virtual whatever container. And then you see it's in the cloud, right? That like if you go build a VM in Azure right now, you'll see this option like click secure boot. It's like virtual TPM. Okay, security co-processors, CPU security extensions. So modern CPUs include built-in security extensions that enhance protection at the hardware level. This is like for our data and use protections as well. These extensions provide features such as secure execution modes, memory isolation, and hardware-enforced privilege separation. So CPU security extensions allow certain code and data to run in protected environments that are isolated from the operating system and other applications. This ensures that sensitive operations can continue securely even if other parts of the system are compromised. These extensions are particularly important for protecting credentials, cryptographic operations, and trusted code execution in modern computing environments. A secure enclave. So a secure enclave is a protected region of memory within the CPU that is isolated from the rest of the system. Again, this is more protections for like our data in use, because sometimes now malware and like, execution or injection can actually attack the CPU as well. So secure enclaves are commonly used for cryptographic operations, secure credential storage, and trusted application execution. And the point is that it's supposed to be like separated at the CPU level, kind of at that hardware level. So even if the operating system gets compromised, you're still supposed to have some separation to where that compromise can't get to that secure enclave. Virtual hardware. So virtual hardware security refers to security controls implemented at the virtualization layer to protect VMs and their resources. So, VM escape, VM isolation is how we protect against VM escape, or just applying, honestly, like virtual machine protections, guys. You do the same thing you do for any server, hardening, defensive depth approaches, HIDs, HIPs, EDR, XDR, the list can go on and on, what we talked about already. But what is unique about virtual machine? They have a hypervisor, and that hypervisor more than likely has a console or panel that lets you deploy these VMs and control and manage these VMs. So if you're using ESXi, that's vSphere. So we got to protect that. So there's more security with a VM than if you just take a regular computer. And we say more, it's just the attack surface increases just a little bit because you're sharing resources. So if one of you gets exposed, the whole hypervisor could be exposed. If it does a VM escape, then all the other virtual machines are exposed. So it's almost like its own little use case of lateral movement within a single system. Okay, host-based encryption. This refers to encryption that's performed by software running on the host system rather than like maybe running it straight into HSM or something like that. This approach is commonly used for full disk encryption, file level encryption, and protecting sensitive data at rest. So you could say BitLocker does this. You do like volume level encryption. So on, remember not really old school, but Windows machines, you could go to the MMC, you can make like your own volumes and drives, and one could be encrypted and then your regular like C drive doesn't have to be. That's host-based encryption. And then your cryptographic keys, the actual keys, could be stored in something like your TPM, or like, it could be like an offline HSM, but you don't really want, not an offline, but like connected in your network somewhere. But typically you're doing host-based encryption, you want everything on that single host. And that's really, we're talking about like FDE there, right? Full disk encryption. So self-encrypting drives, something that's important in our CSFC implementations, right? A self-encrypting driver said is a storage device that automatically encrypts all data written to it using built-in hardware encryption. Encryption is always enabled and is transparent to the user and operating systems. So in self-encrypting drives, encryption keys are stored within the drive's hardware and never exposed to the host system. So if the drive is removed from the system and connected elsewhere, the data remains unreadable without proper authentication. Secure boot. We've talked about this a lot. That's like UEFI. I'll just read some of the slides to make sure I didn't miss anything. Secure boot is a security mechanism that ensures a system boots only using trusted and digitally signed software. During the startup process, firmware verifies the digital signatures of the bootloader, operating system kernel, and other critical components, just like I talked about. And sometimes those validations, that hash, whatever it is stored in like a TPM. Or it could be stored directly like on the, I don't know what piece of the motherboard, but it doesn't have to be a TPM, just an example, right? Measured boot. So measured boot extends the concept of secure boot by recording cryptographic measurements of each component loaded during the boot process, and then those measurements are stored in a TPM for later analysis. So secure boot versus measured boot. Measured boot is more cryptographic measurements rather than just like a hash of like the OEM, like in the examples I use. Oops, sorry about that. Self-healing hardware. So self-healing hardware, let's read this. Refers to systems that can automatically detect failures, corruption, or tampering and recover to a known good state without manual intervention. It's pretty cool. I've never configured this myself, but this includes firmware rollback to a trusted version, automatic restoration of corrupted components, and isolation of damaged subsystems. I've done something similar to this, like with containers, like container images. Not necessarily with like corruptions, but just like, if it's not like working properly, just go ahead and like with an Ansible script, run it, delete it, download a new container image, and then within that same script, deploy the code of that new container image and web application, and let's see if that's not freezing on us or something like that. So there's just an example of something like that. But this is talking about more hardware, so, drives. Tamper detection and countermeasures. So this is very important in our organizations, right? Like if you're doing like a Tempest solution, you want to have tamper detection you want to be made aware if someone, took your travel kit and tampered with it. You want that tamper detection, whether that's a little alarm, a little light, whatever the case may be. Happens with our KGs a lot, right? So tamper detection mechanisms are designed to identify unauthorized physical access or manipulation of hardware components. These mechanisms are especially important in high security environments where attackers may have physical access to devices. Even in our server rooms now, like Dell, the Dell Power Edges you buy now, or the EMCs, they'll have some tamper detection too, even if it's just a red little light that goes beep or something like that, Did I miss one? No, okay. Firmware tampering. So firmware, let's kind of define that first, what firmware is, because I think a lot of times we get this confused. Like even I just had a buddy who's been in networking a long time, not really at an enterprise level like me, and he knows he always has to update his Cisco iOS, his operating system. He was so far behind in one. He was on he said 3 something, and he had to upgrade his ROM and firmware up 3 levels to even get back to I think 15 level iOS XE. So what I'm saying there is that firmware exists even below the operating system. And sometimes your firmware has to be updated, and then that, because that's going to connect to the kernel and then to the operating system. So sometimes it's that lower level even that we can't just apply anti-malware, antivirus directly to, because that's maybe just for our operating system. So let's go over it, right? Firmware is low-level software that controls how hardware components operate and interact with the system. It executes before the operating system loads and is responsible for initiating devices, enforcing configuration settings, and preparing the system for normal operation. Because firmware operates at such a foundational level, it is implicitly trusted by higher layers of software. And that's true, right? Because firmware tampering is something that's hard to do. It's hard to exploit it. Not impossible. It is a target. It is a part of the attack surface. But since it sits so low, it's not as big as the operating system, which is doing everything for the user and connecting and making itself vulnerable just inherently, right? You're using a computer, you go to websites, whatever. So firmware tampering occurs when an attacker modifies his low-level code to insert malicious functionality. This could involve altering motherboard firmware, network card firmware, storage controller firmware, or embedded management interfaces. So what's the danger of this? Hard to detect, and then it's always there. Now, every time you boot, whatever you do, it's there because it's persistent. It's at that low level. It's inherently trusted. So the most serious risk of firmware tampering is persistence. Reinstalling the operating system, replacing storage drives, or restoring backups does not remove malicious firmware because, again, it sits below that. So they can maintain long-term control over a system. Really hard to find. China does this to us, though. Back in 2015, AWS was just building all these data centers. They got all that money, getting a lot of their components from China. And guess what they found? At the motherboard level, which at the firmware level, was backdoors. Right? So it took them a while to detect that. Eventually they did. But that's a company we trusted with our first iteration of, GovCloud. So supply chain. Anyways, shimming. So shimming is a hardware attack technique in which a malicious intermediary device is placed between 2 legitimate components to intercept or manipulate data. The term shim refers to the thin layer inserted between devices, often designed to be small and difficult to notice. A common shimming scenario involves inserting a device between an input peripheral, such as a keyboard, and the computer. The shim captures data as it passes through, allowing attackers to record keystrokes, credentials, or other sensitive information. If this is happening in your environment, you got a bigger problem than just this attack, right? Well, we got an insider threat problem or you got some physical security problems. I've never even heard of this before I built these slides. I was like, what is this? Okay, but definitely heard of USB-based attacks being in the DoD. So a USB, it's an external media device, and essentially what this is if someone inserts malicious code into a USB, drops it in your parking lot, this is the classic cybersecurity story. Don't pick up random USBs in the parking lot and plug them in our computers. But it's a stereotype in cybersecurity and a thing because it's happened before. It's happened where USBs have known to be plugged in. They deliver a malicious payload either by someone that is malicious or by accident, and then you're infected. Now, how do we protect against USB-based attacks? Obviously, the social engineering scenario is user awareness and training and education, but it could be disabling. It could be only using authorized USBs that have that, it's not like a Mac, but it's like a little code that is put into your DLP or HBSS system enterprise-wide that says, yes, you can plug this USB into this computer or old computer, it just depends, right? But sometimes it's the opposite where you register the computer to a certain USB as well. So we had to do that in our environments. We had to do iOS upgrades. And iOS's just don't fit on Blu-ray discs anymore. And if they do, it's like we're using so many Blu-ray disc players. So we have an external 2 terabyte hard drive. They already get approved by Cyber. I don't know if it was like an ETP we needed, but essentially saying only this one can be plugged into our systems here. So I can't go buy one from Best Buy and plug it in. It'll trigger, right? BIOS and UEFI attacks. So the BIOS and UEFI, that's responsible for initializing hardware and starting the operating system. So attacks and BIOS and UEFI attacks involve modifying firmware to execute malicious code during the boot process. So again, it's really just like another firmware attack, but specifically targeting the BIOS and UEFI systems and components of that boot process. Now, again, if this happens, why is it bad? Why is it different than like just malware on the operating system? Because if you're infecting the boot process, which is supposed to be like the start of that root of trust, you know, it's going to be hard to detect and you probably won't even know. Memory attacks. So memory attacks target a system's random access memory. This could be things like buffer overflow, memory injection attacks. Again, so let's continue, which holds data and instructions currently in use. Unlike data stored on disk, memory often contains sensitive information in plain text, including passwords, encryption keys, and authentication tokens, right? Because when you're using a compute resource, you usually don't, you need plain text. You need to be able to read it. That's the whole point of decrypting encrypted messages when it gets to your endpoint. So if an attacker is able to get to that memory, they're going to be able to see everything. So attackers may exploit hardware vulnerabilities or use physical access to read memory contents directly, doing like memory dumps, you know, dumping it even in hex and then trying to convert it. So some techniques leverage direct memory access capabilities of connected devices to bypass operating system protections and extract data without authorization. There are protections against this though. I think we go on about this later, but there's something called ASLR, that's address space layout randomization. That's a data in use memory protection for CPU and memory. Then there's something called XN and NX bits that you can just turn on your systems. They do the same thing. It's just memory protection. I think XN is like AMD though, and NX is CPU. So again, not like specifically RAM, but you know, the RAM, CPU, compute components they protect. The ASLR is specific to like memory. Okay, and then let's go over this EMI. You know, this has happened actually to me, like, you know, in the Army, in the field, we go out and like we place it too close to a generator. Like we get like we get what's called CRC errors on our switch. And it was like, we're like, oh, let's move that cable. Because, you know, we were lazy privates. We didn't like using the Cat6 with like the actual protections because it was hard to make those cables. Well, you know, it's a pain in the ass because you have to cut a lot of shit. And then, you know, that was my lesson. Like, we should probably just use the protected cables better. But anyways, EMI, electromagnetic interference, refers to the disruption of electrical systems through electromagnetic signals. EMI often occurs naturally due to environmental factors. It can also be intentionally generated by attackers. And this is if you ever worked in like an embassy, the Tempest stuff. The Tempest stuff literally is completely built. Every peripheral is built into a system on a Tempest computer that it can't fall victim to EMI because that's how it's built and protected. And it's like its own unique peripherals and things like that. So in a security context, EMI can be used to disrupt system operation, induce faults, or interfere with communication between hardware components. Proper shielding, grounding, that's what you got to do. And like, I have been like at some of these, well, back when we were in the Middle East a lot more, like, you know, these data centers that get spun up on these fobs that weren't grounded properly, and you go in there, you're getting shocked. And they're like, yeah, sometimes we have drop packets, we can't figure out why on our switch and things like that. And like, I never really could prove it, but I'm like, this isn't grounded. Like when I do a show interfaces, they're always getting these CRC and like input errors, and they shouldn't. The cables are made correctly. Like, yeah. I mean, I agree, bro. When I put up the antenna, sometimes I'm like, dude, come on, fuck it, let's just get this shit up. You know, we gotta pass our Valex, you know. But in like data centers, when you start getting bigger and bigger, like it is important to ground it. Not even just like the equipment, whatever. Like you'll get shocked, like for sure. But where are we going now? EMP. An electromagnetic pulse is a sudden, high-energy burst of electromagnetic radiation capable of damaging and destroying electronic systems. This is what I used to tell the ground force commander when SATCOM wasn't up. I'm like, yeah, it's like the solar flares, you know, EMP, it's crazy. But from a threat perspective, EMP attacks represent a high-impact risk that can render systems inoperable by damaging circuits, corrupting firmware, or permanently disabling components. That was a long one, guys. 24 slides. So let's do our quiz. Okay, let me get set up on my other side here. So we are doing the quiz for domain 3.4.1. Okay. Question 1. A cloud service provider wants to allow customers to verify that their virtual machines have not been tampered with during startup. The provider needs a mechanism that records cryptographic measurements of each boot component so that system integrity can be verified after the system has started. Which hardware security techniques best fulfill this requirement? So there are two options. It's A or B. That's, startup options here. It's like the boot options. C and D, obviously not. Secure Enclave just isolates in an operating system on a drive. CPU security extensions are just protecting that CPU. So let's see why we think it's A or B. Oh, records cryptographic measurements. Okay, there it is right there, right? What they said the difference was, secure boot still validates, but it doesn't take cryptographic measurements at the startup or for the state. So that's going to be B, measured boot. Yep, awesome. And we didn't even need like the cloud provider to, for that. It's just whether you're on your desktop or in a cloud, that's fine. Let me bring this up. All right, question 2. A financial institution uses a centralized system to manage cryptographic keys for digital certificates, transaction signing, and encryption across multiple applications. The organization requires strong physical tamper resistance, automatic key destruction if tampering is detected, and compliance with strict security standards. So we're doing something big enterprise. We need something that's going to serve an enterprise that has to do with encryption keys. So off rip, it's not going to be a secure enclave. It's not going to be a virtual TPM. Now, you could argue that the TPM, we're going to apply TPM across the distributed system, but it's just, you're not going to do that, right? So when it's big, encryption, enterprise-wide, across multiple applications, we want something dedicated. So that's going to be an HSM. That is going to be a hardware security module. Okay, question 3. Bring this up on the other side. All right. An organization is concerned that attackers could gain physical access to stolen laptops and attempt to extract sensitive data by removing the storage drive. So we need some sort of encryption on those drives. The organization wants a solution that ensures all data on the drive remains encrypted at all times with minimal performance impact and without relying on operating system for encryption. So I'm pretty sure like full disk encryption. Yeah, does it rely on an operating system? Yeah, because BitLocker is only for Windows, right? It's not like I can use BitLocker on Linux. So it probably rules out FDE. So which hardware security technology best addresses this requirement? Yeah, it's going to be C, self-encrypting drive. That's the only thing really on there, right? Hardware-based encryption that is always active and transparent to the operating system. Okay. Yeah, it's the only thing that makes sense. All right, awesome. Yeah, and some of these questions, guys, like I feel like the answers, are not similar at all. But remember on CompTIA's test, not that I can actually talk about what's on the test, right? But it probably won't be that easy. So, but you guys are answering these pretty good. All right, awesome. Ooh, that was a long one. Yeah, that's why like a lot of these CompTIA tests, I always tell my students, 'cause I've been doing this for quite some time now. You guys seem pretty bright just from the interaction in the chat, but I work with privates, and I always tell them like a lot of these tests are like reading comprehension and just deductive reasoning, like process elimination. It's like almost like a skill taking the test itself rather than like being an expert in all the technologies, right? So yeah, process elimination. I agree. Oh, it's another long one. Do I want to take a break? No, let's just power through. Yeah, let's just power through. Okay. I can't be moaning and groaning like that. I'm excited. I'm excited to be here and teach you guys this stuff. But sometimes I wish I could teach guys like you, like, CCNA, CCNP, stuff like that. It's a little bit more fun. We can do labs. Okay, so domain 3.5.1, given a set of requirements, secure specialized and legacy systems against threats. Okay, so here's all the objectives we're going to go over. Cool, we're going to touch on OT now. As much as, it's funny because I've been teaching this a while, so I've learned OT through like a certain perspective, but I've never worked in like OT environments, obviously. Sometimes you can almost say DoD may function a little bit like that. Like I've definitely been on DoD networks that like seem legacy as fuck, but eventually you life cycle, it's not dams and things like that. So maybe some of you guys have, you can chime in. Okay. Yeah, so this is all the objectives we're going to go over. Supervisory control and data acquisition, that is SCADA, that is part of the operational technologies. So SCADA systems are used to monitor and control large-scale industrial operations such as electrical power distribution, water treatment facilities, pipelines, and rail systems. So SCADA systems are legacy. Like, obviously we can build a new electrical power plant, and maybe we'll have some new technologies in there, but a lot of times it like almost gets built with like legacy technologies where SCADA systems don't even use Ethernet. They use things like POP3, or not POP3, DNP3, and other actual like layer 2 encapsulation methods other than like Ethernet, 802.3. So they were designed decades ago when cybersecurity was not a consideration. They don't have a lot of encryption added onto them because a lot of times they need like that atomic timing to like deal with whatever sensors they're dealing with. So they don't want to add more encryption on top and encapsulate more of their packets. So it just wasn't built with it. It wasn't built with a lot of detailed logging. They'll have like what they call a historian server. Sometimes OT, the language changes. It's a historian server. It's just their logging. It's their journal. But it wasn't really built with that in mind. So as we go into an OT system now, as cybersecurity professionals, we look at SCADA, which SCADA kind of gets built like this: the human-machine interface, the sensors, and then the actual controls. And they talk, sensors and the actual like equipment talk to each other, and then that gets relayed to the human-machine interface. And before that, you have all the servers there, whatever servers in the OT environment. So as we go to secure that, where do we start to secure it? We start to say, where can we add encryption? Where can we add authentication that won't disrupt production from our sensors to maybe like our servers, or down to like the bots or robots or the actual like equipment or tools? So securing SCADA systems requires careful planning. Security controls must protect the system without disrupting operations. And common strategies include isolating SCADA networks from corporate IT networks. And that's the basic architecture, That's something that, a junior cyber engineer in an OT environment knows, is that the SCADA, the OT environment, should not touch the enterprise. If you guys were on the East Coast, when did this happen? Was I still in the Army? A pipeline got hacked, and then people were going crazy. They were going to the gas pumps and putting it like in plastic bags. It just happened on the East Coast. But that pipeline got exploited, if you read the story, because of that. Because the pipeline OT systems somehow, some way had like a connection back to the regular enterprise. So think you guys accessing your Outlook, that's IT. You're on Nipper, you access Outlook, you go on your share drive, that's IT. OT is like all these sensors and things that were being managed on that pipeline actually pumping the oil, and that got exploited due to lateral movement from the IT environment. So a lot of times these OT environments, you want air gapped. Think of like CCTV. I've never seen CCTV in big compounds that's directly connected to like Nipper or even like Sipper. It's its own closed off thing with its own like security guards that are watching it. Kind of similar, you air gap it. Okay, ICS, so industrial control systems. This is just a broad category that includes SCADA systems along with all these other things, PLCs, programmable logic controllers, distributed control systems, or other factory automation technologies. They're responsible for controlling machinery, industrial processes, and critical infrastructure. So what I just talked about was SCADA. I'm going to talk about ICS. You still need that network segmentation that is air-gapped. And if you can, you want to put in the network level protections like encryption and then some like IAM if possible, as long as it doesn't disrupt production. HVAC and environmental control systems. So I don't know, have you guys seen those data centers where like your UPS is actually like SNMP monitored now, so it gets an IP address. Your HVAC systems will actually be IP address. They'll give it an IP address and you can manage it via SNMP. So like in your SolarWinds or whatever you're doing SNMP, you can actually look at this stuff. But it's very important that we upkeep with it because like especially in data centers, you need those hot, cold aisles. You need that cool down effect from all those just servers that are running and blowing that heat. So heating, ventilation, and air conditioning systems are increasingly network connected and integrated with building automation platforms. So from a cyber perspective, obviously we need those things to keep our systems highly available. That's part of our job as cybersecurity. Think about availability. Think about it, not always maybe configuring it, but at least guiding people to making sure our architectures are available and we don't hinder that. But if they're IP connected, that increases the attack surface. And more than likely when the HVAC vendor built their thermostat that's IP connected, do you think they added AES 128 encryption and SHA hash passwords and its embedded fucking Linux purpose-built system there? Maybe it's Linux, OpenBSD, whatever it is. Probably not. So we still need to understand the regular hardening that comes along with this. Disabling admin default credentials or changing them if that's all we have. Applying encryption where we can. And then you have to monitor it, right? If it's going to be connected to your network, we have to monitor it. And probably maybe put in some compensating controls if there is no inherent security at all. IoT. Everything I just talked about, apply it to IoT. IoT increases our attack surface. We segment it. It's inherently probably insecure because if I'm building a smart TV, a smart fridge, a smart washer, I'm not worried about encryption. They just lack basic inherent security. So you put in compensating controls because part of your risk management is, okay, this is increasing our attack surface a lot because if this is easily exploitable if someone's inside the network, if they can from the outside. So we want to harden it as best we can, isolate it as best we can while still making it available for why we put it on our network in the first place. I always say put this on a guest network if they're going to connect them via Wi-Fi. That IoT belongs on a guest network or its own IoT network that is literally just for those things, and that's it. Don't even expose that. Well, whatever. Hide the SSID, but, segment it. Okay, system on a chip. So a system on chip integrates multiple computing components such as processors, memory, networking, and storage into a single physical chip. So this is just, for our small form factor devices, just boop, and you get what would you get on a computer motherboard? That's, RAM, special CPU, GPU, networking interface card that sits on the motherboard, the PCI, whatever. Instead, all that goes on a single chip. So security challenges with SOC-based systems include limited visibility into internal operations, vendor-specific firmware, because you kind of get vendor lock-in because you can't go to the RAM vendor, CPU, Intel, it's just like everything's on that chip. So whoever made this, it's like, that's what we have to go with. Embedded systems. So embedded systems are dedicated computer devices designed to perform specific functions. Examples include medical devices, automated control modules, industrial sensors, and smart appliances. So that's when, again, we have like maybe a purpose-built Linux that's extremely lightweight just for these tools to get, they need an operating system. They're doing a specific function, but they're not like user-friendly. You're not going to, download Outlook on them. Maybe some of those medical tools, but, that's not the point of them. They're purpose-built. So again, when things are purpose-built, if it is Linux, you can still harden Linux the regular way while not trying to kill like the availability of it. But some of them may not have the updated systems. Maybe they build an embedded system on a stable Linux kernel from 2009. And now that's when you're interacting with. It's not like Ubuntu, it's not Debian, it's like a straight Linux kernel. So security strategies for embedded system focus on minimizing exposed interfaces, controlling physical access, and restricting network communication. That's always something we can do. You can put it in that isolated VLAN. You can monitor that network really well. You can put a tap on that so you can inspect the traffic on that. Wireless technologies and radio frequency. Okay, go a little faster. So many specialized and legacy systems rely on wireless communication technologies such as Wi-Fi, Bluetooth, Zigbee, cellular networks, or proprietary RF protocols. So when it's wireless, anyone can connect to it. If I can figure out the frequency, I can connect to it with the right antenna, with the right modulation capabilities, if I have the right things to listen to that spectrum, listen to that frequency. So when we're connecting to a lot of devices using wireless, that's something we have to understand. So it may be used in a lot of physical processes, an 802.11, 2.4 gigahertz range. And if we can't put Wi-Fi protected access on there, we at least have to do some signal monitoring. But when we can, always add strong encryption to those control frames, to those join frames of 802.11 or RF. Because, with wireless technology, we're worried about things like evil twin. With RF, we're worried about things like jamming or like spoofing an RFID chip. Okay, security and privacy considerations, segmentation and monitoring. So segmentation is one of the most important security controls for specialized and legacy systems because that's maybe all you can do. Maybe you can't patch it. Maybe, it's end of life. If it's an OT environment, that's what you have to do. You got to keep it away from the IT environment. So that's where we start getting real comfortable using jump servers, firewalls, VLANs, physical and logical isolation. Continuous monitoring. Because we know it's legacy, guess what? It's even more important for us to monitor it, especially if it's something that's kind of well exposed. Maybe it has to be because it's part of production systems, right? Aggregation, hardening, and data analytics. So aggregation involves collecting logs, alerts, and telemetry from multiple systems into centralized platforms. How many times have we talked about this with SIEM, log aggregation? But with OT environments, you don't forget those fundamentals as well. And again, it may be, not that it's more important, but because we can't implement XDR, we have more time to focus on something like that, aggregating logs. And guess what, guys? If you harden in the cloud, if you harden in IT, you harden as best you can for these legacy OT systems. We do that, it's simple. It's not patch updates, because we can't do that. It's just disabling unused ports protocols. Data analytics. This allows organizations to analyze large volumes of monitoring data to identify trends, anomalies, and potential security incidences, that heuristic analysis. So here again, behavior analysis and machine learning, if it can do it for the cloud, it could do it for IT, more than likely you can do it for OT. Now, that's a bigger discussion, I feel like. I don't want AI in my power plants, but anyways, that's not part of the exam objectives. All right, environmental, regulatory, and safety considerations. So this is something that may be a little bit different. If you're just, let's say you're Dunder Mifflin Paper Company, you may have some environmental and safety regulations you have to abide by in your warehouse and things like that. When it comes to the IT systems that a cybersecurity professional may have to be aware of, that's a different story. Now, when we talk about environmental factors, that is something we have to worry about because where we're placing our equipment, we have to be aware of the humidity, the dryness in the air, the cold or hot temperatures, and how we operate at super hot temperatures, how we operate at super cold temperatures, especially with like us in the military. I know we're kind of getting off track. We're talking OT, but like with our edge compute systems, trying to do all this Palantir, Andro lattice mesh nodes, all these C2 communications at the edge. How do we operate in those environments that are like the Middle East? So Fort Warren at the NTC, how do these edge compute nodes actually function at heat and at temperatures? It's something important to think about. Okay, so attackers may exploit environmental controls to disrupt operations or damage equipment. You mess up the HVAC in your data center, you're kind of almost doing a denial of service, right? Because some servers are going to go down from overheating. Okay, regulatory. So many specialized systems operate in highly regulated industries such as healthcare, energy, transportation, and manufacturing. Regulations may indicate how systems are secured, monitored, and documented. So that's what does come into play. If there's regulations, we look for the cyber part of it. We look for the IT component of it. Even if it's a lot of EPA and stuff like that. Like, don't dump your stuff, your hazardous shit. Okay, safety. Safety is a primary concern in operational and embedded system environments. Security controls must never introduce the risk that could endanger people or damage equipment. And that's why OT is sometimes difficult, right? Because we can't have our cyber solution that we implemented stop production or change the way production happens, where a robot arm's coming this way for 10 years, we implement something and then it bugs out and all of a sudden it's going the opposite way and it hits somebody. Obviously that's an extreme but plausible scenario, but That's essentially what we're worried about here. And that's just IT in general, and we're part of that equation too if we're trying to implement some new cyber thing onto the operating systems and embedded systems that operate this potentially dangerous machinery or equipment. Okay, industry-specific challenges. So we're about to just go through all the different industries here, okay? Which we've kind of done already in previous sections, but let's do it. So utilities include power generation, electrical distribution, water treatment, natural gas, and wastewater systems that support daily life and national stability. So what are we concerned about here? Power outages, water contamination, or gas system failures can affect entire regions and create public safety emergencies. So because of this, we need to make availability and safety are prioritized above confidentiality, and security controls must be applied cautiously. Kind of just what I've talked about. Transportation. So transportation includes, air, rail, and road travel, shipping ports, and public transit networks. This is becoming important, right? With the advent of like self-driving things, or like our trams that are like self-driving. So cyber incidents in transportation systems can have immediate safety implications, including collisions, derailments, or loss of situational awareness. This is that one car. Have you guys seen those self-driving cars? They have them in my hometown in Phoenix and like San Francisco. The Waymo? But there's been cases of the AI, the system like kind of pretty much bugging out, like locking people in. Yeah, it's crazy. We can actually look it up. We can break this up. It's like self-driving cars. Yeah. Waymo. Yeah, thank you. Yeah. Let's just go news, see if we see anything. Yeah, there we go. First thing. Continue to pass stopped school buses. So, cybersecurity, why do we care about that? Not only because, all these things are a loss of trust in the company, and then things get real bad eventually. Politics comes in and they say, no, maybe we don't want these cars because they're a danger. And maybe you applied that patch to this car that made it pass a stop school bus. Just things to think of when we're in these OT environments, right? So we apply things cautiously, and maybe we do, and in some sense, need strong encryption authentication, because imagine if that thing got hacked. But again, we don't want to bug it out or bug things, and there's going to be probably rounds and rounds and rounds of testing on it. Well, you hope there is. Yeah, I've never taken one. They have them in my hometown, but I don't know. I don't trust it. Because you can't take control. That's the other thing. You can't take control of it. Not ready for robots to take over my life. All right, healthcare environments. Healthcare environments combine traditional IT systems. Let me see, robotaxi. Let me look that up. Are they operating? Let's see. I think I've heard this. Yeah. Of course, all these sites, they hating on Elon Musk. That's cool though. See, I wonder if we can buy this. It'd be nice if you could buy this. But I will tell you, if you could, that'd be sick to use. Because you imagine your commutes. If you could just have the car drive yourself, you could live like an hour and a half away. You get up and you just sleep in the car. That would change things. That'd be nice. Okay, sorry. We keep being distracted. We got fucking a lot of slides. Okay, healthcare. So, again, pretty much the same thing applies. These critical life-saving applications and systems, you can't just go patching and securing it, because we CASP scan in a hospital. I bet we get a lot of highs. And you go to the IT department, you need to patch these. They're like, well, they're doing surgery at 3. You know what I mean? Like with us in my environment, they're like, you need to patch this right now. It needs to get done right now. Our ATO depends on it. I'm like, okay, calm down. But in these healthcare systems, and really all these systems, when things can be life-threatening, we have to cautiously think about how we're applying, where we're applying, and how we're applying it. We don't want to be too secure and then disrupt the availability, because that's the most important thing in these systems, which is why things like network segmentation and monitoring become even more important, so we can be proactive in seeing if something malicious is happening on the network, rather than hardening these devices to a point of they're not operable. And then manufacturing. So manufacturing environments depend on industrial control systems, robotics, and automation technologies that operate production lines. These systems are designed for precision and uptime, often running continuously with minimal tolerance for interruption. Cyber threats to manufacturing include operational disruption, intellectual property theft, and sabotage of physical processes. A compromise in a single component can halt an entire production line, resulting in significant financial loss. So, all these are kind of funny. It's just like, yeah, no matter what industry you're in, what's the bottom line? Don't fuck up the profit, don't mess up, just your little cybersecurity. We know that it's important, but we only care once we get data breach, then we're like, okay, make it. We got to start hardening. But it is true, like I'm not meant to make fun of it like that. And all these industries, there is specific challenges, and a lot of them relate around we need to be operable. So if what you're going to apply may secure us, but may hinder our operability and our availability, it may not want it. Then financial. So financial institutions rely on complex systems to process transactions, manage accounts, and support global markets. So the financial sector faces constant attacks from cyber criminals seeking monetary gain. So this one is, CIA is important across the board. You need it all. You need confidentiality, integrity, and availability are all critical. Now, I'm sure we don't need that atomic timing in this like we do in healthcare. Well, who knows, stock market. What's more important than money, right, guys? But we're going to impose strict IAM here. That's what really is going to happen. And a lot of auditing standards. And that's why there is so much auditing, like SOC Type 2 in the financial industry. The SEC and things like that does play a role now in even the cyber part of our financial institutions and transactions. So when we have legacy financial systems, organizations typically surround them with modern security controls rather than modifying the systems themselves. And of course, you're dealing with money. So it's compensating controls. If you have legacy systems in any of these sectors, we always implement compensating controls that monitor, harden as best we can, disable protocols as best we can. Government and defense. Here we go, guys. We can talk about this all day. But government and defense systems support civilian services, law enforcement, intelligence, and military operations. So these environments often involve classified information, national security concerns, and highly capable adversaries. How do we secure in the Defense Department? We got NSA, we got NIST, CSF, RMF, we got the DODI publications that tell us exactly how we're going to apply cybersecurity. We got the 8140 compliance chart. We have ISSMs, ISSOs, ISSCs that do all of our information assurance for us, that do our hardening, that scan for us. So, security strategies in the government, they don't really worry about profit, right? We, as a system integrator, so you guys are GDIT, you're on that mission training center, you guys don't have to work at quarterly revenue earnings. We just don't as employees. So we can actually take cybersecurity a little bit more serious because it's our national defense, and we're not trying to turn a profit like us. Like GDIT obviously is on the contract, they're winning the contract, and they're going to try to, get as much money as they can out of that. But your performance improves that contract, but we're not working at quarterly statements, profit margins, seeing how to properly distribute money to cybersecurity technologies because it's kind of already there for us, right? It's maybe built into the contract. So that's government and defense. Okay, unable to secure. So industry-specific challenges. We're not able to patch. We're not able to update. So with those specialized legacy systems, we're not able to secure them themselves. So what do? We accept the risk. So in part of our risk management matrices, we're going to say we have to accept the risk because we can't do nothing about this. Maybe the third-party application that we're using that's critical, was built on this legacy system and we cannot upgrade. So we're going to compensate. We're going to put it behind a firewall. We're going to put it behind ACLs. We're going to put a lot of monitoring on it. And we're going to do compensating controls. I'm going to keep repeating that because, obsolete systems. So obsolete systems, what's the difference between that and legacy? Well, let's see what it says. Obsolete systems rely on outdated hardware, operating system, or protocols that are no longer considered secure. Vulnerabilities in these systems are often well documented, making them attractive targets for attackers. So replacing obsolete systems can be risky and expensive, especially when they are tightly integrated into larger environments. Okay. Unsupported. So unsupported systems no longer receive vendor patches, security updates over time. CompTIA is funny. Like, isn't this all just the same? Legacy, unsupported, obsolete. They all have the same challenges, in my opinion. They can be vulnerable. It's not going to be able to patch. So what do we have to do? We have to compensate for ourselves. Okay. Let's move on. Highly constrained. So highly constrained systems have limited processing power, memory, storage, or bandwidth. Okay, this one's a little different. And what we're saying here is that maybe we don't have the ability to vertically scale. Maybe we don't have the ability to vertically scale. Maybe they don't make that motherboard anymore that's like compatible with RAM, and maybe it's old RAM that is only compatible with it. Whatever the case may be, it's highly constrained. So we have to be careful with adding our security features because we need it to be functional. So if we add more encryption, where is it storing those keys? How much CPU, how much RAM function out, like memory is that taking? How many CPU cycles are we adding to that? So adding security features may impact performance or interfere with real-time operations. As a result, many standard security tools cannot be deployed without unacceptable side effects. So security strategies for constrained systems emphasize simplicity and external protections, narrow level controls, minimum configurations, and predictable behavior are prioritized to maintain stability while reducing risk. Let's go. We got through it. Definitely taking a break after this one. The Robo-Taxi. I like the graphic on that, though. I'm not like I didn't like the Cybertruck, but this one seems pretty cool. I like how it looks like Cyberpunk on it. All right, sorry. Let's go to our quiz. Okay, so we're taking the domain 3.5.1 quiz. Let's begin. Question 1. Okay, we're there now. Which characteristic most clearly differentiates operational technology environments from traditional information technology environments when designing security controls? Okay, let's read this again. OT from IT, okay, when designing security controls. So what did we talk about that whole slide pretty much, which differs, right? It is a different approach, is that we need this shit up. OT, we need this shit operational. So I'm going to go with D here. Operational technology environments prioritize system availability and safety. Yeah, because, in IT, I'm not worried about, my laptop falling on me and then I'm, messed up for life. I always think of those oil rig workers. When I watch those videos, I'm like, man, that is crazy. That's what I think about safety. Like, they can fucking get hurt for life. Their backs are probably destroyed. All right. Question number 2. An organization deploys a large number of IoT devices that have limited processing power and cannot support advanced security software. Which security strategy is most effective for managing risk in this scenario? A bunch of IoT devices, so hey, we got to isolate those bad boys, put them in their own VLAN. We got to, disable, we got to harden them as best we can. So let's look at our security strategies. So A, installing endpoint EDR? No, not on IoT devices. They have limited processing power, so not, of course not. Relying solely on vendor default security, no. Disabling encryption makes no sense. So yeah, C, using network-based controls such as segmentation and traffic inspection. Yeah, we're monitoring, we're isolating, doing the basic things we need to do when implementing IoT. All right, question number 3. An organization relies on unsupported legacy systems that are critical to daily operations and cannot be replaced in the short time. Which security principle is most appropriate when managing the risk associated with these systems? All right, let me scroll down, sorry. All right, let's read these. Eliminating all known vulnerabilities before allowing system operation. No, it's legacy, right? So unless you're going to hire like 5 software engineers that know computer science actually to do patches and updates, good luck. Accepting unrestricted access to maintain operational efficiency. Some environments, I'm sure that's what happens. But really, with legacy, like I've been saying, you compensate. You try to reduce the attack surface as best you can. With an OT environment, they still focus on availability. But yeah, we're going to go C here. It's going to be C. Reducing exposure through compensating controls and monitoring. All right, awesome. Question 4. A regional electrical utility operates control systems that were installed over 25 years ago and cannot be easily patched or rebooted. The organization is concerned about increasing cyber threats but must avoid service disruptions. Which security approach best aligns with these operational constraints? So pretty much we're not updating those. We're just not. And so now we need to again compensate for that, and we gotta do something. We gotta harden as best we can. And if this is all network-based traffic, we're kind of worried about is like our attack surface, our exposure. We're gonna want to monitor heavy. So we're pretty much doing a network approach here rather than like endpoint application approach. So let's see. Deploying EDR? No, of course not. There's not. If it's 25 years ago, there's no EDR that can even probably be deployed on there. Isolating control networks, implementing continuous traffic monitoring, possibly. Probably gonna go with that one. Replacing with cloud-based platforms? No, we're not gonna do that. Not in an OT environment. Applying frequent operating system updates during peak operational. Oh yeah, of course not. Okay, so yeah, the best answer here is B. Isolating control networks and implementing continuous traffic monitoring. Okay, question 5. An organization operates a manufacturing facility that uses industrial control systems which must run continuously and cannot be frequently patched or rebooted. The security team wants to reduce cyber risk without interrupting operations. Which approach is most appropriate for securing this environment? So most OT systems are going to be, they're going to be similar. Like we said, monitoring, compensating, segmentation. We're beating a dead horse essentially, but I kind of like it because it's like that's what we have to understand at this level. We're not going in and, to these utilities and power plants and all of a sudden, what's time to learn, DNP3 and all these other protocols. In the other CASP, they like went over all these protocols that are in OT, and I'm glad they kind of took it out because it's like, we just need to know this at a high level because now they make certs like in the IC squared that are specific to like OT environments. But yeah, B, you're right, Masood. The only thing that applies to OT. Awesome, 100%. I need to take a break. I want to rest my voice, guys, but let's see what we got. Domain 3, we got 1, 2, 3, 4, 5. Okay, I think we can get through domain 3 today. We can do it. Domain 4 is a little shorter. That's why tomorrow, we'll definitely finish up domain 4. Okay, yeah, let's take a 10-minute break. Okay, guys, let's go ahead and get started again. So now we're going to move on to domain 3.6, given a scenario, use automation to secure the enterprise. So now we're going to go over scripting, IAC, configuration files, and cloud APIs. And we're going to talk about how we can use them to automate security. Okay, so we'll be going over everything in red here. Now remember, high level. So we're not going to teach you how to code in Python. I'm not going to teach you how to do a cron or scheduled task. We're just doing this at a high level. I probably should have got some of these up here because we could have examined at least some YAML and XML, but it's okay. And then cloud API, software development kits, webhooks, we'll go over that. And then generative AI, we'll go over how it can help us with coding and documentation. Okay, so PowerShell. PowerShell is a powerful scripting language and automation framework primarily used in Windows environments. So in enterprise security, one thing with PowerShell is you don't want to give admin access to everyone because you can easily develop a malicious script in PowerShell that if you gave admin privileges and someone knew how to execute remote signed and stuff like that, they could, attack you. Now, what we can do in cybersecurity operations in PowerShell is we can gather logs, we can automate like the log divings, we can automate user account creation, user account deletion for our audits. So it's a critical tool in securing our environments and also just administering our environments as well. Okay, Bash. So Bash is a command line shell and scripting language for Linux. So the Bash shell, everything you do with PowerShell in Windows, you can do in Bash and Linux. It's completely different, obviously, because this is the default we use for Linux, but in security automation, Bash scripts are often used to monitor file integrity, check running services and processes, and are, all the same shit. Parse logs, automate patches and updates, manage firewall rules such as IV tables or NF tables is all done from the Bash shell. And then Bash is, the cloud is built on Linux as well, so those Bash skills you can easily translate to like AWS or GCP console line as well. It's all Linux, right? Okay. And then typically if you create a Bash shell that needs to be run at a certain time, you do that with like a cron job. Or you execute it with like a cron job that schedules it out. Okay, Python. Python is a programming language that can be used in so many different ways. I use it in network automation. We use Python, the NetMiko library specifically, to connect to our Cisco iOS devices and Palo Alto devices to run scripts. So it is not tied to an operating system. We can use Python. It's supposed to be interoperable with everything. It's an interpreted programming language. So some examples, so like for security tools specifically, SIEM, SOAR platforms, vulnerability scanners, expose Python software development kits, or support Python-based extensions. What I mean by that is we can use that as a language to automate a lot of the remediation, patching automation as well, and to interface with these API-enabled security appliances, modern security appliances. Okay, so cron jobs. That's a time-based job scheduler. When I say jobs, it's just like your script, whatever you want to do, shut down a service, shut down the entire system. You can do that with a cron job in Linux. Scheduled tasks is the Windows version of that. Task scheduler, I've used that a lot actually when I used to run like test centers and stuff to run the, it wasn't Bash. What is it in, anyways, a script in Windows. It's not PowerShell. It's going to mess me up now. What is it called? Anyways, to run scripts, and this is like GUI based, where cron job is like you use like Vim or Nano to actually edit the cron jobs and the scheduled jobs you may have. Where scheduled tasks is like GUI based, you find the executable that you want to run at Monday at 8 a.m., right? Okay, event-based triggers. While scheduled automation runs at predefined times, event-based automation runs in response to something happening. So event-based triggers are essential for rapid threat response. So examples of security relevant events include a failed login threshold being exceeded. So that can even be like, 3 failed logout attempts. We can automate a way to send an alert to us rather besides just the default like account lockout. So malware detection by an endpoint protection tool and a user account being created or a firewall rule being modified. All these different things can be an event-based trigger to automate the remediation of that event or even to like alert us. Then infrastructure as code. So we've been over this already, but this is where the provisioning, the managing, the updating, the patching of our multi-vendor environment or our enterprise environment of on-prem and cloud, we start to look at it as a single piece of code, and that when we make change, we do what developers do. We create a DevOps pipeline of the platform we have, the code we're using. We integrate security into that because it's a cybersecurity class, of course, and we start to automate that scaling, that provisioning of our infrastructure. This is typically done by like SREs, site reliability engineers, platform engineers, DevOps engineers, things like that. And when we talk about cybersecurity and infrastructure as code, we have to understand the tools and code that we use to make sure it's not exposed to external third-party libraries that could have vulnerabilities, and that we're doing things in a secure way with secure protocols, things like that hard-coded API keys. We want to make sure we're implementing key vaults, maybe some code signing, and then making sure we're still in compliance with our organizational policy when implementing the infrastructure as code. Getting into the source control manager, making sure our GitHub is protected, multi-factor authentication to get to it, making our branches private and protected. Like configuration files, we have a lot of different types of configuration files. So we have YAML, yet another markup language, what it's called. This is the basis for Ansible too. Ansible is all in YAML. And a modern Linux, a lot of the configuration files like DNS.conf, DHCP.conf, networkinterfaces.conf is all YAML format now. It's just a human readable data serialization format. XML is a structured markup language. It's used in a lot of legacy systems, enterprise software, and security tools. I mean, Palo Alto's configuration file, like the 1420s that we use, is still XML based. You know, I throw that into VS Code. I have my XML extension, you know, and we can do like a div config tool to look at it compared to other like Palo Altos, you know, so it's not totally antiquated. XML can be used in a lot of network automation as well for like Cisco IOS. JSON. So this is another serialized data format, but this is lightweight, and this is using all the API exchange, right? So from front end to back end, and when we go to the SQL database, we get that SQL code, we reformat it into JSON, and that gets put into our HTTP and REST API requests, and that's that human readable format that we take to our front end, and then build out our buttons and everything on the front end of our website. You know, so JSON, JavaScript object notations, what it stands for is the typical format for reading anything in security and network and systems automation, okay? So an example, right? So, no, I don't need to put an example, it's fine. But security automation frequently relies on JSON to send and receive API requests, define security policies, represent logs and alerts, and exchange data between tools. You know, so if I'm building a REST API to interact with the cloud, and I want to look at a log event, and that log event has to get transferred to me, you need to transfer it somehow. It's going to be via HTTP. It's not going to be maybe always a downloadable file that's nice and pretty for you. It could just be that raw data. And when it sends you raw data without putting it in a data serialization format, because you're not downloading maybe a text file or like a YAML or some sort of comp file, you want to put that in JSON. And then you can use Python and a lot of different coding techniques to take that JSON format. You can export that to HTML. You can, you know, interact with it in a way that's used widely by everyone. There's all these tools and frameworks and libraries built to interact with JSON to make it in a very easily digestible way for you. Okay, TOML is a configuration file format designed to be simple, minimal, and unambiguous. It is often used in application configuration, security tooling, and infrastructure and deployment systems. Okay, cloud APIs and software development kits. So APIs in the cloud are the same. They serve the same purpose and function as APIs anywhere, at any third-party software application or even on-prem. Why do we care about them in cybersecurity? What have we been talking about APIs and the dangers of them when it comes to increasing attack surface? It could be insecure, and we want to do rate limiting or rate monitoring on it because we don't want it being exposed to like DDoS. So that's APIs. Whether we have that on-prem, third-party software, in our cloud-specific environment and tenants, it's all the same kind of security we want to do. And then SDK, software development kits. These software development kits, a good example of this, when you purchase something on our website, Stripe is our e-commerce like transaction provider. I can't think of it right now. It's what does the transactions for. So like I have to go to my Stripe dashboard, I can see all my sales, whatever. We had to get an SDK for Node.js, because that's our backend. That's what we use to code our website. We have to get the software development kit from Stripe and integrate that into our website to be able to use Stripe like hosted internally for us, right? It's called the software development kit. So why do we care about that in security? Well, if we're using like a third-party vendor that may not be in compliance, but with our specific industry, it may do something, make server function, but maybe we're so regulated that maybe partners, other department, not departments, but like partners, other corporations can, but we're on this specific program that says, no, we have more strict regulations. So we have to be aware of that. We just have to be aware of these companies, their software development kits, and what they're approved for within our compliance, and make sure there's nothing vulnerable about them inherently. Okay, webhooks. So webhooks are a mechanism for delivering real-time notifications between systems, very similar to how APIs interact, but it's not an API. So instead of one system constantly pulling another, a webhook allows a service to send an immediate message when an event occurs. We used to use webhooks a lot in our network automation in my last unit I was in, where if we went on our Ansible Tower front end, we'd run an Ansible playbook. That was the trigger to send a webhook over to our IPAM, IP address management system in Nattlebot. It was the event trigger to send a webhook over to GitHub or GitLab so we could get the source code, import it into our Ansible playbook, get the most up-to-date playbooks, and then the webhook to the Nattlebot would say, hey, expose this, API. Then we do an API call to it. We go get the IP address information, insert that into our variables. That was our most up-to-date source of truth. And then we build the configuration file, right? So just a little example of how we can use webhooks that are event triggered, but it doesn't have to be a manual press of, us pressing a button on the front end of our Ansible Tower web GUI. In security automation, this can be used to trigger SOAR from the SIEM platform. So we could have SIEM monitoring, notice some deviation from the user baseline, boom, webhook to our SOAR appliance, and now it's running a playbook to remediate something that's potentially malicious. Okay, generative AI and security automation, code assistance and documentation. So generative AI can assist with writing automation scripts, debugging existing code, and explaining unfamiliar scripts, and translating logic between scripted languages. And this, from a network engineer perspective, this has been something that's great for us, and even from a cyber perspective, because I'm not a programmer. I've learned Python. I've gone through these courses in the past. I've built these stupid little games in Python and stuff, and I just did that to increase my ability to do network automation using Python. But if you don't use it, you lose it, and there's been periods where I'm not focused on network automation. I'm doing more like traditional network deep dive troubleshooting, and you lose some of the skills. So the great thing with coding is you could be a solid CCIE level network engineer. I'm not saying that's me, but you could be with not the best automation skills, but you have AI to assist you now. Now, it's not going to say it's going to do everything for you, but you can put in there, hey, I need to use a Python.NET Miko script to build VLANs and do some zero-touch provisioning on new switches. It could build that script for you. You may have to fine-tune it. You may need some help, and it may not be perfect, but you can get there now. Easy. So it's been great in that code assistance. And then documentation. Let me show you guys something. Obviously, it's not ever going to be used on the DoD. We'll never say never. But have you ever heard of an application called Scribe? It is awesome. It automatically builds documentation for you with clicks. So you see how it's capturing over that on the right? And then you can complete the capture. I love this company. And then it literally builds a how-to for you with images already there, with the clicks there. You can hit done editing, and you can share it. Oh, I don't want to get Scribe Pro. But anyways, if I still paid for Scribe Pro, I could export it to a PDF. I could export it to Markdown, right? But anyways, yeah. So that's imagine being a help desk person and having to build all these how-tos for users and stuff, other help desk technicians. This would be amazing to be used. I swear I'm not sponsored by them. I just think it's awesome. Okay, quiz time. Okay, domain 3.6.1 quiz. All right, question 1. A security team wants to automatically disable user accounts when repeated failed login attempts indicate a possible brute force attack. The organization wants this action to occur immediately without waiting for a scheduled scan. Which automation approach best meets this requirement? Let me turn on the chat. Hold on. Disable user accounts when repeated failed indicate a possible force. So we gotta it's gotta be event based. Maybe it's a webhook or whatever it is. It doesn't have to be a webhook, but it's an event-based trigger. So let's look at our answers. An event-based trigger tied to authentication failure thresholds. Oh, that's probably it right there. A cron job that reviews, no. That's not trigger-based, once per hour. A scheduled PowerShell script that runs nightly, no. It's not trigger-based. A configuration file defining a password compatibility requirements. Yeah, event-based. Yeah, it is like an EEM applet. Yeah, we used to use EEM applets all the time in my old job, based off syslog messages, like the mnemonics, you know? But yeah. An event-based trigger tied to authentication failure thresholds. All right, question 2. And we use them we tie an alias to an EEM, so we would just type in if we were downrange, because training on our nodes back in the rear, our hubs would be in the States, and that's where our call manager would be, and their ICE servers, the PAN, whatever. And then we'd go, let's say, to the Middle East, and now the tunnel configuration changed, and now we're going to hubs in the Middle East. So instead of a whole new configuration, we would just run an alias Middle East, and the EM applet would build the tunnel for that region with its correct IPsec and whatever tunnel destination, tunnel sources, and things like that. Yeah, use those a lot. And fucking ChatGPT writes them really good too, to be honest, those EM applets. Okay, question 2. An organization uses infrastructure as code to deploy its cloud environment. During a security audit, the team discovers that all firewall rules, encryption settings, and identity permissions are defined in version-controlled files. What is the primary security advantage of this approach? Infrastructure as code to deploy its cloud environment. During a security audit, the team discovers that all... Yeah, version control. So version control, that's awesome. That means you always know you're on the same sheet of music everywhere. Faster deployments. Yeah, of course, faster deployments. Elimination of need for security monitoring tools. Of course not. C, consistent, auditable, and repeatable security configurations. That's probably going to be it. Yeah, let's go with C. Consistent, auditable, and repeatable security configurations. Question 3. This is the last one? Yeah, I think so for this quiz. Yes, yeah, making a baseline for everything, which is good cybersecurity as well, because then it's easy to, imagine, even for STIGs, we always talk about this in my day job, trying to get to a good baseline. But STIGs, we have to do it per site in production, hardening. Imagine if we had literally one baseline that was all the same. You would only look at one running config, and that's it. But anyways, what do I know? Okay. Question 3. A security engineer is writing an automation script that must collect data from multiple cloud services, analyze the results, and make decisions based on conditional logic. The script must also be portable across different operating systems. Which scripting language is best suited for this task? Yeah. Just like we did in SOF. Sorry. Across multiple... Oh, Python. Yeah, it's the only one there because, yeah, Bash is Linux, cron is for Linux, and PowerShell is for Windows. Even though you can technically put PowerShell on Linux now and stuff and MacBook, but it's, yeah. Awesome. Let's go, guys. 100% again. Let's do it. Okay. 3.6.2. Okay, so now we're going to go over domain 3.6.2, Given a scenario, use automation to secure the enterprise. Automated patching, SOAR, vulnerability scanning. So we're going to go over everything in the red. This one, I don't know if I asked you guys. I don't know if you guys deal with fucking like your cyber a lot and automating STIGs and all that shit, but this is something I use a lot now in this day job because we patch, any of the vulnerability scans in the network equipment. I've used Oval when hardening a RHEL server because I've had to, I built my own RHEL server so I could do network automation. So, but anyways, I'm sorry. Just go over this shit. I don't need to tell stories all day. Okay, automated patching. So be careful with this though. I will say automated patching is a good thing in the sense of like, scalability, stability, whatever. But if a new patch comes out, you don't automatically deploy it right away, right? You gotta test it. You gotta see what it affects, yada yada. So automated patching is the use of software tools and scripts to automatically identify, test, deploy, and verify security patches. This is talking about just verifying. That would work, but the deployment is after you do all the testing. Don't just automatically do it. But obviously patching, I think what this is trying to say is like, once you do that, once it's good to patch, instead of doing it manually, going computer to computer, you want to do it in an automated way. Whether that's a PowerShell script, whether that's from Microsoft Intune, that's something that like the private sector uses, like MSPs use that now to manage all their customers' Microsoft Windows and versioning control. It's really nice, web GUI, but that's what we want to do. And that's not just for endpoints, that's for network devices, that's for systems and servers, containers, virtual machines. Auto containment. So auto containment is the automated isolation or restriction of a system, account, or workload when malicious or suspicious activity is detected. Instead of waiting for manual intervention, security tools automatically apply containment actions to prevent further damage. Examples of auto containment include isolating an endpoint from the network, disabling compromised user accounts, blocking malicious IP addresses, quarantining files, shutting down compromised virtual machines. So this is saying, hey, instead of us having to manually do this, maybe we have some sort of system. Maybe it's a SOAR, maybe it's a playbook, maybe it's SIEM doing it, maybe it's IPS doing this for us, where we enable some sort of automatic feature for containment. Okay, here we go. Yeah, SOAR, runbooks, and playbooks. So let's go over this. So SOAR platform, it stands for Security Orchestration, Automated or Automation Remediation. So SOAR platforms combine security tools, automation logic, and incident response workflows into a single system. What we mean by that is just from a single place, you can run all this, and you can integrate that into your SIEM systems. You can integrate it into your endpoint security tools like XDR, and you can build your playbooks and runbooks in your SOAR application to, protect all those devices I just talked about. So runbooks are documented step-by-step procedures that describe how to respond to specific types of security incidences. Traditionally, runbooks were written instructions that analysts followed manually. Yeah, so like runbooks used to be like, if you had a really fucking high-speed SOC, like flow chart of everything to do an incident response, and it was like a pretty much a really good SOP, but it was like, oh, this happened, go grab that runbook from our content management system, which is still a thing you should still do, but now there's some more automated ways to do it. Playbooks are the automated execution of runbooks. So there you go, right? While runbooks describe what should be done, playbooks actually perform those actions using automation. And again, that could be trigger-based, it could be ingesting logs, so many different ways we can do this that we've described. Vulnerability scanning and reporting. So this, we do this. We do what's called Nessus scans, we call it ACAS, and then we get those reports and we upload them to EMAS, and we do that on a weekly basis to say, hey, we're being proactive in our vulnerabilities and protections and stuff like that. So vulnerability scanning is the automated identification of security weaknesses in systems, applications, and networks. Scanners compare system configurations and software versions against known vulnerability databases. Automated vulnerability scanners run on scheduled or continuous intervals, cover large numbers of assets, produce consistent results, and generate reports that prioritize remediation efforts. Yeah, like when we get our scans too, we filter in what's the highs, what are the highs, who has the highest CVSS score, it gives us a CVE, so then we go to the CISA website, look at the CVE and say, okay, here's how we fix this, and it's usually just a patch, it's just, all right, we got to do an iOS upgrade to fix this. Because I'm in networking, so it's always like iOS. Okay, so now let's go over the different ways that we can do hardening actually in a government environment. This relates to like STIGs and STIG libraries and checklists and stuff like that. So SCAP, Security Content Automation Protocol. I use this to automate the hardening of my Rails server. So the Security Content Automation Protocol is a standardized framework used to automate vulnerability management, configuration assessment, and compliance checking. The Open Vulnerability Assessment Language, OVAL, defines how to describe system configurations and test for vulnerabilities. We'll move on from that, it's fine. Extensible Configuration Checklist Description Format, XCCDF, defines security configuration benchmarks and compliance rules. During this slide, when I have privates, usually I'm like, okay, hey guys, like, I'll send you some YouTube videos to learn this. If you want to go be an ISSE or an ISSM or whatever in the, not an M, an O in DOD, you know this shit, STIGs, ACAS, you're like fucking good to go if you know for the most basic like cyber job or entry level cyber job. Okay, sorry, CPE, Common Platform Enumeration, provides a standardized way to identify hardware, operating systems, and applications. CVE, Common Vulnerabilities and Exposures. Sometimes I say enumeration, it's just a fucking thing I have. I know it's exposures, but if you ever hear me say that, I apologize. CVE is a publicly maintained list of known security vulnerabilities. Each vulnerability is assigned a unique identifier, allowing vendors, security tools, and professionals to reference the same issue consistently. And that's true. You know, we always reference the CVE. And the CVE will actually tell you, too, in there, like, was this a network-based attack, you know, system-based attack, things like that. Then the CVSS score provides a standardized method for scoring the severity of vulnerabilities. And there's a lot of different factors that go into the CVSS score that we could go over, like the base, temporal, environmental. That's like the, you know, the default 3. All right, cool. I want to show you guys something real quick though, just in case, on my YouTube channel. Hold on. Not Cisco switch install. Or let's just say automate STIG checklist. So I made a video on how to automate STIG checklist for Cisco IOS XE. So if you guys ever have to do this, create checklists or checklist CKLBs, I have a video like walk the dog, like going to the NavC website. It's on the Intel link, and going through running this on PowerShell and automatically building your checklists for like iOS for the NDM, like network device management, and like the layer 2S or like the layer 3 iOS XE STIG checklist. So just since we're on the topic of it. Okay, let's do our quiz. I think we're at 3.6.2. Yep. All right, let me bring up my other screen here. An organization detects that a user's endpoint is actively communicating with a known command and control server. The security team wants to immediately stop the potential spread of malware while further investigation is performed. Which automated security capability best addresses this requirement? Let's see. A known C2. And they want to immediately stop it. Automated. Okay, yeah. Auto containment. That's the easy one. All right, question 2. A security operations team wants to ensure that incidences such as phishing emails, malware detections, and suspicious logins are handled in a consistent and repeatable way, regardless of which analyst is on duty. They also want many of the response steps to occur automatically. Which solution best fulfills these goals? I see you guys. D. These answers must be easy. Or these questions must be easy because you're answering quick. But yeah, SOAR. It's going to be SOAR for this one. Response steps automatically, right? Question 3. A vulnerability scanner reports that several systems are affected by the same known software flaw. The security team wants to prioritize remediation based on how dangerous the vulnerability is, including how easy it is to exploit and the potential impacts to systems. Which standards provides this type of severity? Okay. Common vulnerability, severity scoring. So yeah, that was a gimme right there. Severity scoring. Okay. Yeah, common vulnerability scoring system. That was an easy one. Hey, we're still keeping our 100% streak alive. So let's go. All right, awesome, guys. Now let's move on to domain 3.7.1. Okay. So domain 3.7.1, explain the importance of advanced cryptographic concepts. Let me bring up my thing here. Okay, so we're going to be going over advanced cryptographic concepts. So I loved, like, in the old cast they talked about post-quantum like taking over as well, but I don't know if it's happened yet. You know, I don't know if all of our encryption is obsolete just yet. But just before I get into this, just know if like post-quantum and quantum computing, if they can crack our current bit standard encryption, don't you think post-quantum computers could also create a new encryption standard that is like, you know, so just want to talk about that before we get into it. Okay, post-quantum cryptography. So most modern secure communication rely on public key cryptography to exchange keys and verify identities, stuff like Diffie-Hellman, elliptic curve cryptography. You know, this is our secure key exchange. This is when we do asymmetric encryption, and then we take the public and private keys, combine them from between client and server. We do secure key exchange using one of those algorithms like Diffie-Hellman or elliptic curve cryptography. We get a unique shared key, then we use that unique shared key that's just unique between our session, and we do symmetric encryption. And that's like the standard for internet browsing. All that communication is based on bits, guys, the computer language. What I mean by that is like, you know, that's binary. You know, all that's done in computers in binary. But with quantum computing, it uses qubits. And I don't know the math, but imagine the power of 2 is like binary, and now imagine things in the power of 4, okay? A lot different. So quantum computing introduces a fundamental threat to these systems because a quantum algorithm, known as like Shor's algorithm, in theory can efficiently solve the mathematical problems with that Diffie-Hellman, RSA, which is asymmetric, and elliptic curve cryptography depend on. So all we're saying is that quantum computing can crack our current encryption algorithms that aren't quantum, that aren't using these qubits, that don't have the same mathematical logic. Okay, so resistance to quantum decryption, or let me actually read this slide. So post-quantum cryptography refers to cryptographic algorithms designed to resist attacks from both classical and quantum computers. The goal is not to replace all cryptography, but specifically to protect the public key mechanisms used for key exchange and digital signatures. Symmetric encryption and hash functions are less affected by quantum advances and can usually be strengthened by increasing the key size. So there we go. So resistance to quantum decryption attacks means that even if an attacker has access to a powerful quantum computer, they cannot feasibly recover encryption keys or forge digital signatures. Because, you know, when we're doing encryption, there's two key components. It's the algorithm, you know, it's that math there that's actually going to, you know, change things through ciphertext. And then it's the key you need to like lock and unlock that door. So if we can figure out a way that protects just that secure key exchange that's needed for us to have this global end-to-end encryption internet, you know, global communication, HTTPS, we need to protect at least that. We need to at least protect that secure key exchange. So, okay, where was that? Access to a powerful quantum computer, they cannot feasibly recover encryption keys or forge digital signatures. Post-quantum algorithms are built on mathematical problems such as lattice-based, hash-based, and code-based constructions. So in practice, organizations are beginning to adopt post-quantum cryptography cautiously. I know in Palo Alto, like if you ever read like NSA, CSFC, like requirements, it's, you know, if you want to go to bed, you know, just read that shit. But Palo Alto advertises they have post-quantum, you know, capabilities. So it is becoming like on the market like that, you know, not as big as the AI fucking tag on everything market, but you know, it's getting there. Okay, key stretching. So key stretching exists because humans create weak secrets. Passwords are typically short, predictable, reused, and frequently exposed in breaches, which is easy, right? You know, those rainbow tables where, oh yeah, I did a SHA-256 hash, but then it's like, okay, well, I can just look up what password 123 hash is in SHA-256, Control F on your fucking whole password, you know, database I just took that's hashed, and oh, I see it. I see the hash I just made over here. I see it over here. I know what your password is now, you know? So key stretching transforms a low entropy input, such as a password, into a strong cryptographic key by applying computationally expensive operations. It's kind of like salting, right? But this process intentionally slows down password guessing attempts and uses a random salt value to ensure that identical passwords do not produce identical keys. So there's the fix. What I just described, there's the fix right there in key stretching, where if I take the input of password, run SHA-256 against it, and I take the input of password and run SHA-256 against it again, just like that, just simple, no key stretching, no CMAC, no HMAC, no salting, I should get the same output. But if I don't put that random, if I don't do that, I get the same output. And that's when we're exposed to like these rainbow table attacks and stuff. But if I do add those random variables that don't equate to my password, we add to it, then we get different hash checksums and digests. And then we're not vulnerable to those types of attacks. Key splitting. So key splitting addresses the risk that a single compromised system or individual could expose critical cryptographic secrets. Rather than storing a key in one place, key splitting divides the secret key into multiple parts so that no single piece is sufficient on its own. So, when we talk about like the private keys, like let's just talk about asymmetric encryption. When we make those key pairs, private, public keys, the private key is always supposed to be stored somewhere private, secret, that no one's supposed to access. And then if that key does get exposed, you're boned, because that's everything, that's how we do this relationship of asymmetric encryption. One encrypts, one decrypts, and the private key is supposed to be secret so that we can trust, that when we use the receiver's public key to encrypt, whatever, So key splitting helps us prevent the exposure of that private key, right? So one common approach is threshold-based key sharing, where any required number of shares can reconstruct the key, but fewer shares reveal nothing. Key splitting can also be implemented operationally by separating key material across different systems, environments, providers. While this increases complexity, it significantly reduces the risk of key compromise. It's a little dramatic in my writing, I know, catastrophic key compromise. All right, guys, so when something is ciphertext, can we process it? Typically, the answer is no. We got to decrypt that, turn it into plain text, and then we can process it. Think about a database. If it's encrypted, we got to, we still got to get the unencrypted version of that to, make queries against it or whatever. So homomorphic encryption. Homomorphic encryption allows computation to be performed directly on encrypted data without first decrypting it. The result, when decrypted, matches the outcome performing the same computation on the plain text. So why is this important? This is important in environments where data confidentiality must be preferred even during processing. So like cloud-based analytics on sensitive data. This kind of became popular in the cloud, so where we want to process our own data in the cloud tenant, but maybe we want to use the cloud managed encryption keys and it's encrypted, we want to leave it encrypted, Forward secrecy. I talked about earlier, simultaneous authentication of equals in WPA3 gives us this, so let's read about it. Forward secrecy protects past communication from future key compromise. Without forward secrecy, an attacker who records encrypted traffic today could decrypt it later if they obtain the long-term private key used by a server. So, it's like the old school replay attacks, we prevented that a long time ago, but it's like, well, if I captured this, I captured the key exchange, I captured all these things, now I wait for the private key to become available to me, or I break it, or whatever the case may be. But forward secrecy helps us against that. So forward secrecy ensures that each session uses unique ephemeral keys that are not stored long-term. Even if a server's private key is compromised, previously recorded sessions remain secure because their session keys cannot be reconstructed. Hardware acceleration. I don't know why. So strong cryptography can impose heavy computational costs. That's why we say we use symmetric encryption to encrypt large data payloads. It's why it's the final step in that TLS cipher suite, TLS exchange, because all that data in transit we're pushing, full disk encryption is usually symmetric. So as we increase the key size, as we increase things to protect against, this post-quantum and all these different attacks, and just, the landscape changes and things get more vulnerable, we may need to do some hardware acceleration to be able to manage our resources in a way to build these strong encryptions. So modern CPUs include specialized instructions that accelerate encryption and hashing. Dedicated hardware such as TPMs or HSMs provide secure storage and cryptographic operations isolated from general purpose systems. So that's again when we have a dedicated appliance to do that kind of stuff. So beyond performance improvements, Hardware acceleration enhances security by limiting exposure of key material and enforcing strict access controls. Okay, performance versus security. So we've talked about this all of class, right? It's just availability versus confidentiality. They call it performance versus security. So we got to define it because that's what was in the CompTIA exam objectives. So the security does not exist in isolation from operational realities. Bang your line, right? As much as we try to harden and secure and apply encryption, it has its consequences. Where things become less available, where more power is required, more computational resource, more processing power. Maybe we're adding too much encapsulation onto the packet and we increase latency and we start getting fragmented frames. So it could impact the user experience. But however, if we have weak cryptography, that could lead us to exposure like data breach and things like that, which could have long-term effects than maybe a user waiting an extra 20 seconds. It's definitely hard in today's environment when we have this instant gratification and TikTok's algorithm queues up 5 videos you think you'll like automatically before you even go to the next swipe up, or Instagram or wherever your poison is. It's hard in that environment to sometimes deal with like a user base or even a customer base that doesn't understand why something may take a long time. It's because we might leverage, harden. We're cybersecurity focused. So that's why we have things like hardware acceleration, dedicated HSMs. At least that's something we can do for the computational load just for encryption and at least the keys. Secure multi-party computation. So secure multi-party computation enables multiple parties to jointly compute a result while keeping each other's parties' input private. No participants learn more than the final output. This technique is valuable when organizations need shared insights without sharing raw data. Use cases, collaborative analytics, probably like community cloud, privacy preserving fraud detection, and distributed trust models. Authenticated encryption with associated data, AEAD. So authenticated encryption with associated data combines confidentiality and integrity into a single cryptographic operation. In addition to encrypting data, AEAD ensures that any tampering is detected. Mutual authentication. I don't know why I keep double clicking, sorry. Mutual authentication requires both parties in a communication to verify each other's identity. Rather than only authenticating a server, both the client and server prove who they are. This is critical in enterprise environments where internal services, administrators, and automated systems must trust each other without relying on network location. It's kind of like that subject to object relationship we're talking about in Zero Trust, where it was just like we authorize and authenticate the subject and then it can access the object resource. This is saying like, well, we need to do both ways, right? So mutual authentication prevents impersonation attacks and supports Zero Trust architectures, right? So both pass through that policy enforcement point because that object still has to be authenticated and authorized on the network just as much as that subject does. Okay, quiz time. And then we'll take another break, guys. All right, hold on. Okay, question 1. An organization is designing a secure communication system intended to protect sensitive data for the next 20 years. Security engineers are concerned that encrypted traffic captured today might be encrypted in the future if cryptographic algorithms become vulnerable to quantum computing. Which cryptographic approach best addressed this concern? What you got, Masood? B. Let's see. Increasing RSA key sizes, disabling. No, we don't disable symmetric encryption. Using post-quantum cryptography or hybrid key exchange mechanisms. That's going to be your answer. That's what literally the slide said. So yes, we're going to go with B. Using post-quantum cryptography or hybrid key exchange. Yeah, 20 years. I don't know. That's a little. Well, you think that's a little too long? You don't think in 5 years something new may come out? All right, question 2. Let me post it in here. A cloud service provider Maybe a little sooner. I agree with you. Well, who knows, man? This AI bubble might pop, man, and the whole market might change, and who knows, who knows. But it doesn't stop universities from researching. You are right. A cloud service provider wants to encrypt millions of customer objects while maintaining centralized control over encryption policies, auditing, and key rotation. The provider also wants to limit the impact if a single encryption key is compromised. Okay? Which cryptographic design best satisfies these requirements? Okay, I don't think we talked about envelope encryption. Did I miss it in my slide? Now I'm like, hold on. Let me check something, guys. Sorry to bump off it. Did I miss that? Hold on. We definitely didn't talk about that, right? Must be. Okay, I'm gonna make a note of that. Okay. All right, so let me read this again. Sorry. A cloud service provider wants to encrypt millions of customer objects while maintaining centralized control over encryption policies, auditing, and key rotation. The provider also wants to limit the impact if a single encryption key is compromised. So this to me reads like key escrow. Which cryptographic design best satisfies these requirements? Encrypting all data with a single master key. No, that's the whole point. Is we don't want to be compromised by one key. Encrypting each object using asymmetric encryption with unique key pairs. And C, envelope encryption using data encryption keys and key encryption keys. And key splitting across multiple administrators without centralized management. Yeah, we're going to go with C. I agree with you. Even though we didn't go over, let's read this. So this scenario highlights a common challenge in large-scale systems, managing encryption securely and efficiently while minimizing the impact of key compromise. Encrypting all data with a single master key creates a dangerous single point of failure, while using asymmetric encryption for every object introduces unnecessary complexity and performance overhead. Envelope encryption solves these problems by separating responsibilities between different layers of keys. Data is encrypted using fast symmetrical data encryption keys that can be generated uniquely for each object or session. These keys are then encrypted using higher level key encryption keys managed by a centralized managed system. Key encryption keys. It's another tongue twister. All right, last question here. A security team wants to ensure that the compromise of a server's long-term private key does not allow attackers to decrypt previously recorded encrypted sessions. Which cryptographic property is most critical to achieving this goal? Yeah, we're going to go with A here, right? Forward secrecy. That's what we talked about protecting. Like, that session, it's perfect forward secrecy protects us from brute force and things like that. Awesome. We got another 100%. Okay, guys, what we got here? What we got left? Let me see. 1, 2, 3, 4, 5, 6, 7. Okay. Let me see how long this one is. See if we might just doing too much in one day. I want to add some photos to these tonight too. I don't like it's so dry. Okay, guys, we're gonna end for the day. We just got one more section in domain 3 that we can save for tomorrow because domain 4 is short.